Hello and welcome. I'm truly delighted you're here. Before we get underway, I'd love for you to share in the comments where you're tuning in from and what time it happens to be in your part of the world. It's always such a joy to see this community come together across places and time zones. I also want to take a gentle moment to thank everyone who's subscribed and shown support through likes on the videos. It helps me know what you value most, and it helps others find this space too. Please feel free to leave your ideas for future topics in the comments. Now, let's begin. Chapter 1: Understanding Antimatter, Basics and Definition. Imagine a world where the very fabric of reality is woven with two contrasting threads, matter and antimatter. While we are surrounded by matter, everything from the air we breathe to the stars that twinkle in the night sky, antimatter exists as a curious counterpart, a reflection of the material universe but with a twist. Antimatter is composed of antiparticles, which mirror the particles that make up matter but with opposite charges. For example, while an electron carries a negative charge, its antiparticle, the positron, carries a positive charge. This delicate balance of opposites invites us into a fascinating realm of physics. The characteristics of antimatter are both intriguing and perplexing. When an antiparticle meets its corresponding particle, they annihilate each other, resulting in the release of energy in the form of gamma rays. This annihilation is not just a simple reaction. It's a profound event that embodies the essence of cosmic balance. The energy released during this process follows Einstein's famous equation, which reveals the deep relationship between mass and energy, illustrating how a tiny amount of matter and antimatter can yield vast amounts of energy. Imagine the possibilities that arise from such interactions, where the annihilation of particles could illuminate our understanding of the universe or even lead to advancements in energy production. The history of antimatter is a tale of brilliant minds and groundbreaking discoveries. The concept first emerged in the early 20th century, rooted in the theoretical work of physicist Paul Dirac. In his quest to reconcile quantum mechanics with special relativity, Dirac proposed the existence of antiparticles. He famously remarked, "The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are, I believe, simply a consequence of the existence of the antiparticle." His theory was a bold leap into the unknown, suggesting that for every particle, there exists an antiparticle. The first experimental confirmation of antimatter came years later, in the form of the positron, discovered by Carl Anderson in 1932. Anderson's observations of cosmic rays revealed the presence of a particle that behaved like an electron but had a positive charge. This discovery opened the door to a new understanding of the universe, highlighting the symbiotic relationship between matter and antimatter. It was a moment that not only validated Dirac's theory, but also sparked a cascade of research into the exotic properties of antimatter. As we reflect on the differences between matter and antimatter, we encounter a multitude of contrasts that reveal the elegance of our universe. While matter forms the stars, planets, and living organisms, antimatter remains elusive, existing only in fleeting moments or under specific conditions. The universe appears to be predominantly composed of matter, a phenomenon that puzzles scientists. Why is there so much more matter than antimatter? This imbalance, known as baryon asymmetry, raises profound questions about the origins of the universe and the fundamental laws governing it. Could there have been conditions in the early universe that favored the creation of matter over antimatter? This question lingers in the minds of physicists, inviting exploration and speculation. Antimatter is not merely a theoretical curiosity, it plays a pivotal role in the field of physics. It challenges our understanding of the fundamental principles that govern the cosmos. Researchers actively explore antimatter in laboratories around the world, seeking to uncover its secrets. The CERN laboratory, for example, is home to the antiproton decelerator, a facility designed to produce and study antimatter. Here, scientists create antiprotons and positrons, carefully capturing them to observe their properties and interactions. This research holds the potential to yield insights into the fundamental forces of nature, the origins of mass, and even the very fabric of space-time. Imagine the implications of harnessing antimatter. The energy released from the annihilation of matter and antimatter could one day provide a nearly limitless source of power. In a world grappling with energy crises and environmental concerns, the allure of antimatter as a clean fuel source is tantalizing. However, the challenges of producing, storing, and manipulating antimatter remain formidable. Currently, it takes an immense amount of energy to create antimatter, far surpassing the energy we could hope to extract from its annihilation. As physicist Robert Forward put it, if we could harness antimatter, we would have a fuel with a power density 1 billion times greater than hydrogen. As we delve into the mysteries of antimatter, we find ourselves at the intersection of science and philosophy. What does the existence of antimatter tell us about the universe? Are we alone in our understanding of reality, or is there a vast, untapped potential that lies beyond our current comprehension? The story of antimatter is not merely about particles and antiparticles. It is a narrative that intertwines with the very essence of existence. The significance of antimatter extends beyond its physical properties. It invites us to question the nature of reality and our place within it. It encourages us to explore the unknown, to push the boundaries of our understanding. In the quest for knowledge, antimatter serves as a beacon, illuminating the path toward deeper insights into the cosmos. Each discovery brings us closer to unraveling the fabric of the universe, revealing the intricate connections that bind us to the stars and the mysteries that lie beyond. In this journey through the realm of antimatter, we find ourselves captivated by the beauty of science and the wonder of exploration. The duality of matter and antimatter reflects the complexity of the universe, reminding us that even in the vastness of space, there are still enigmas waiting to be deciphered. As we continue our exploration, let us remain open to the possibilities that lie ahead, embracing the unknown with curiosity and a sense of wonder. The study of antimatter evokes a sense of awe and intrigue, igniting imaginations and inspiring scientists across disciplines. Its very existence challenges our understanding of reality. As we contemplate the differences between matter and antimatter, we delve deeper into the implications of this dichotomy. While matter composes the tangible world around us, the trees swaying in the breeze, the rivers flowing with grace, antimatter exists as a fleeting specter, often only glimpsed in high-energy experiments or cosmic events. Consider the vast cosmic theater where particles dance in a delicate equilibrium. Antimatter emerges in places like the heart of stars or during explosive cosmic phenomena. In supernovae, where immense energies are unleashed, particles and antiparticles collide, creating a symphony of annihilation. These cataclysmic events serve as a reminder of the power and beauty inherent in the universe, drawing connections between creation and destruction. One might wonder, how does this balance manifest on a cosmic scale? The universe, in its infancy, may have produced equal amounts of matter and antimatter. However, a fascinating asymmetry arose, leading to the predominance of matter we observe today. This enigma, why matter triumphed over antimatter, remains one of the great mysteries of modern physics. Theoretical physicists, including the esteemed Steven Weinberg, have suggested that certain interactions in the early universe could have favored the creation of matter. These hypotheses continue to fuel research and debate as scientists endeavor to unravel the threads of our cosmic origin. The quest to comprehend antimatter extends beyond theoretical musings. It permeates practical applications as well. In the realm of medicine, for instance, positron emission tomography, or PET scans, harnesses the principles of antimatter to visualize the inner workings of the human body. When positrons emitted from radioactive tracers meet electrons in our tissues, they annihilate, producing gamma rays that can be detected and translated into images. This remarkable intersection of physics and healthcare exemplifies how the study of antimatter can yield tangible benefits, enhancing our understanding of health and disease. Now, imagine the landscape of future technologies powered by antimatter. The prospect of harnessing this elusive form of energy for space travel captivates the imagination. Antimatter propulsion systems could theoretically offer a means to traverse the vastness of space at unprecedented speeds. The energy density of antimatter, compared to conventional fuels, is staggering. Such advancements could transform our ability to explore distant worlds, making the dream of interstellar travel a tantalizing reality. Yet, despite these alluring possibilities, the road to harnessing antimatter is fraught with challenges. The production of antimatter remains an arduous task, requiring sophisticated technology and immense energy input. Current methods yield only minuscule amounts of antimatter, far from sufficient for practical applications. Scientists like Walter O'Brien highlight the complexities involved, stating, "Creating antimatter takes a lot of energy, but the potential benefits are astronomical." This paradox encapsulates the allure of antimatter, the tantalizing promise of energy that could reshape our world, tempered by the formidable obstacles that lie ahead. In laboratories worldwide, researchers are engaged in a delicate dance with antimatter, seeking to unlock its secrets. The antihydrogen experiment at CERN aims to study the properties of antihydrogen, the antimatter counterpart of hydrogen. By capturing antihydrogen atoms and probing their behavior, scientists hope to glean insights into the fundamental symmetries of the universe. Will antihydrogen behave in the same manner as hydrogen, or will it reveal unexpected differences? This suspenseful inquiry underscores the broader quest to understand the laws governing our reality. As we ponder the significance of antimatter in the grand tapestry of physics, we also confront philosophical questions about existence itself. What does it mean for our understanding of the universe that there is an opposite form of matter? Are we merely observers in a cosmic play, or do we possess the ability to influence the outcomes of these fundamental interactions? The study of antimatter invites us to reflect on our place in the universe, urging us to embrace the mysteries that lie beyond our current knowledge. In the words of physicist Richard Feynman, the imagination of nature is far greater than the imagination of man. This sentiment resonates deeply as we explore the enigmatic realm of antimatter. It serves as a reminder that our understanding is but a glimpse into a vast and intricate reality, one that challenges us to think beyond the confines of our current comprehension. As we continue to unveil the layers of antimatter, we embark on a journey filled with wonder and possibility. Each discovery, each breakthrough, propels us forward, illuminating the path toward deeper understanding. The allure of antimatter lies not solely in the pursuit of knowledge, but in the endless questions it provokes, questions that have the potential to reshape our understanding of the cosmos. In this exploration, we remain steadfast in our curiosity, for it is curiosity that drives the human spirit. The mysteries of antimatter beckon us, urging us to venture into the unknown with open hearts and inquisitive minds. As we continue this journey, let us embrace the beauty of discovery, for within it lies the promise of enlightenment and the potential to redefine our reality. Chapter 2: How Antimatter is Created, Production Methods. Antimatter, with its mysterious properties and elusive nature, is not only a subject of profound scientific inquiry, but also a product of both the universe's natural phenomena and human ingenuity. Picture the cosmos, a vast expanse filled with energetic events that produce antimatter in ways that both surprise and fascinate us. One of the most intriguing sources of naturally occurring antimatter arises from cosmic rays. Cosmic rays, high-energy particles that travel through space at nearly the speed of light, bombard the Earth from various celestial sources, including supernovae and pulsars. When these cosmic rays collide with atoms in our atmosphere, they can generate a cascade of secondary particles, including antiparticles. This natural production of antimatter is a cosmic dance, a symphony of energy and matter unfolding in the silent depths of space. Imagine the moment when a cosmic ray strikes an atom in the atmosphere. This encounter can unleash a chain reaction, resulting in the creation of positrons, those elusive antiparticles that mirror electrons. Each collision is a fleeting moment of creation, a brief glimpse into the workings of the universe, where matter and antimatter momentarily coexist before vanishing into the ether. The sheer energy involved in these collisions is staggering, serving as a reminder of the powerful forces at play in the universe. Yet, the story of antimatter does not end with the natural occurrences in the cosmos. Human innovation has led us to create antimatter in controlled environments, primarily through the use of particle accelerators. These sophisticated machines are designed to propel charged particles to incredible speeds, close to the speed of light. As these particles collide, the energy involved is immense, allowing for the creation of antiparticles. In a particle accelerator, imagine a scenario where protons are accelerated and directed toward one another. When they collide, the energy of the impact can produce various particles, including pairs of matter and antimatter. This process is grounded in the principles of quantum physics, where energy can be transformed into mass, giving birth to antiparticles. The creation of antihydrogen, for instance, involves combining positrons with antiprotons, resulting in a hydrogen-like atom composed entirely of antimatter. The journey of an antiparticle from its creation in a particle accelerator to being studied by scientists exemplifies the elegance of modern physics. Pioneers in the field, like Carlo Rubbia, who played a crucial role in discovering the W and Z bosons, have paved the way for our understanding of how antimatter can be produced artificially. Rubbia once expressed the thrill of scientific discovery. The most exciting part of science is not the results, but the questions that lead to new discoveries. However, producing antimatter is not without its challenges. The creation of even a small quantity of antimatter requires an astonishing amount of energy, often exceeding the energy that can be harnessed from its annihilation. This paradox raises significant questions about the practicality of antimatter for potential applications, such as advanced propulsion systems for space travel or energy generation. Once produced, the containment of antimatter presents another layer of complexity. Antimatter cannot exist freely in our world. The moment it encounters matter, the annihilation occurs, releasing energy in a burst of gamma rays. To prevent this destructive interaction, scientists have developed sophisticated electromagnetic traps. These devices use magnetic fields to suspend antiparticles in a vacuum, allowing for their study without the risk of annihilation. Imagine a small cloud of antihydrogen, held in place by the delicate balance of magnetic fields, floating silently in a sterile chamber. It is a remarkable sight, a tangible representation of the universe's duality. Yet, the challenges of maintaining such delicate structures are immense. The processes involved in production and containment must be precisely controlled, requiring advanced technology and an understanding of fundamental physics. Despite these hurdles, the quest to harness antimatter continues to captivate the imagination of scientists and engineers alike. The potential applications are as vast as they are intriguing. If we can find ways to produce and store antimatter efficiently, the implications for energy production and transportation could be transformative. The dream of using antimatter as a fuel source, for instance, evokes visions of interstellar travel, where spacecraft could traverse the cosmos with unparalleled speed and efficiency. As we explore these production methods, we begin to appreciate the intricate balance between the forces of nature and human innovation. The universe, with its cosmic rays and energetic events, continuously reminds us of the untapped potential of antimatter. Each moment spent studying this enigmatic substance brings us closer to understanding not only the workings of the universe, but also the possibilities that lie ahead. Consider, for a moment, the elegance of creation. In both natural cosmic events and human-engineered accelerators, antimatter emerges as a fleeting yet powerful entity. It dances in the shadows of our understanding, inviting us to unravel its mysteries and unlock its potential. The journey of discovery, rife with challenges and wonders, continues to inspire generations of scientists to push the boundaries of what we know. Antimatter is not merely a scientific curiosity. It is a testament to the resilience of human inquiry and the boundless curiosity that drives us to explore the universe. Each experiment, each collision, brings us closer to a deeper understanding of the fundamental nature of reality itself. The pursuit of antimatter holds a mirror to our own existence, reflecting the delicate interplay between creation and annihilation, between matter and its elusive counterpart. The exploration of how antimatter is created is not just a tale of scientific achievement. It is a journey into the heart of what it means to be part of this vast cosmos. As we continue to delve into the methods of production, let us remain open to the wonders that await us. For in the world of antimatter, every discovery is a step toward illuminating the dark corners of our understanding. As we immerse ourselves further into the world of antimatter, we encounter the remarkable processes that enable its artificial creation. At the heart of this exploration lies the particle accelerator, a monumental invention that has revolutionized our understanding of the fundamental building blocks of the universe. Imagine a massive structure, reminiscent of a futuristic coliseum, where particles whirl and collide with unprecedented energy. Inside these accelerators, protons or heavy ions are propelled along circular or linear paths, reaching speeds that approach the speed of light. The accelerators utilize electromagnetic fields to guide these charged particles, creating a finely tuned environment where extraordinary collisions can occur. When these particles collide, they unleash vast amounts of energy, a phenomenon encapsulated in the principle that energy and mass are interchangeable. This principle allows for the fleeting birth of antimatter, as energy condenses into particles, manifesting as antiparticles. The creation of antimatter within these machines has been a monumental achievement in physics, marked by significant milestones. One of the most notable successes came from the European Organization for Nuclear Research, commonly known as CERN. Here, scientists successfully produced antihydrogen, the simplest form of antimatter, by combining positrons with antiprotons. The process is both intricate and beautiful, requiring a harmonious orchestration of various elements and conditions. Consider the moment when positrons, generated from radioactive decay or other sources, are introduced to antiprotons, produced from high-energy collisions. These antiparticles come together in a carefully controlled environment where they can form antihydrogen atoms. This creation is not merely a scientific feat, it represents a profound realization of the principles of quantum physics at work. The journey of antimatter production, however, does not end with creation. High-energy collisions, the very heart of particle physics, play a crucial role in this narrative. Each collision can result in a cascade of new particles, creating an ephemeral realm where matter and antimatter exist side by side, if only for the briefest of moments. This phenomenon evokes a sense of wonder as we ponder the implications of these interactions. What if these collisions could unlock new pathways to understanding the universe, revealing secrets hidden since the dawn of time? Yet, producing antimatter in such quantities is fraught with challenges. The energy required to create even the smallest amounts often surpasses the energy we could potentially harness from its annihilation. This paradox presents a fundamental hurdle in our quest to utilize antimatter in practical applications. The thought that the energy needed to produce these fleeting particles might eclipse the energy we could derive from them invites us to reflect on the nature of progress in science. How do we reconcile these challenges with our aspirations for discovery? The containment of antimatter adds another layer of complexity to the story. Antimatter, existing in a delicate state, cannot come into contact with ordinary matter without resulting in annihilation. This presents a logistical puzzle for scientists who aim to study these particles in detail. The electromagnetic traps mentioned earlier are not just clever inventions, they serve as lifelines for antimatter, allowing it to exist in a vacuum, suspended in a field of magnetic forces. Visualize a tiny cloud of antihydrogen encased in this magnetic embrace, suspended in a state of tranquil anticipation, bearing witness to the intricacies of the universe. This scene embodies the pinnacle of human ingenuity, where advanced technology meets the fundamental laws of nature. Yet, maintaining this equilibrium requires continuous precision, as any disturbance can lead to the sudden release of energy in a brilliant display of gamma rays. The challenges of producing and containing antimatter evoke a profound sense of humility. The very act of creation, whether through cosmic means or human innovation, reminds us of the delicate balance that governs our existence. As we delve deeper into the methods of antimatter production, we discover not only the remarkable achievements of scientists, but also the inherent limitations we face. In this pursuit, we find inspiration from the words of visionary physicists who have paved the way for our understanding. Their insights serve as guiding stars, illuminating the path forward. Indeed, the quest for antimatter is not solely about the science. It is a reflection of our collective curiosity, a testament to the unyielding spirit of exploration that has driven humanity from the earliest days of inquiry. The potential implications of mastering antimatter are tantalizing. Imagine a world where antimatter could be harnessed for clean energy, offering a sustainable alternative to our current sources. Envision spacecraft powered by antimatter engines, capable of traversing the vast distances of our galaxy in a fraction of the time it currently takes. The possibilities are as vast as the cosmos itself, inviting us to dream beyond the confines of our current understanding. As we reflect on these production methods, we are reminded of the intricate dance between nature and technology. The universe, with its cosmic rays and high-energy collisions, continues to unveil secrets that challenge our perceptions. Each discovery leads us further down the path of understanding, revealing the interconnectedness of all phenomena, both seen and unseen. In the grand tapestry of existence, antimatter serves as a thread that weaves together the fabric of reality. Its creation, whether through the explosive energy of cosmic events or the painstaking precision of human engineering, invites us to ponder our place in the universe. The journey of antimatter is a testament to the resilience of human inquiry, a reminder that in the face of challenges, the pursuit of knowledge remains a beacon of hope. As we continue to explore the methods of antimatter production, let us embrace the wonders that lie ahead. For in the interplay of creation and annihilation, we catch glimpses of the profound truths that govern our universe, beckoning us to delve deeper into the mysteries that await us. Chapter 3: The Properties of Antimatter, Behavior and Interactions. Antimatter, a mirror to the matter that constitutes our very being, possesses fundamental properties that both intrigue and confound us. At its core, antimatter is made up of antiparticles, each embodying the opposite characteristics of their matter counterparts. For instance, while a proton, positively charged, serves as a building block of atomic nuclei, its antiparticle, the antiproton, carries a negative charge. Imagine a universe where every particle of matter has its twin, a shadowy counterpart that exists in a world of opposite charges. This duality is not merely a quirk of the universe, but a cornerstone of the laws of physics, revealing a symmetry that governs much of our understanding. When it comes to the behavior of antimatter, one of its most fascinating aspects is its annihilation upon contact with matter. This encounter is not a gentle meeting, but rather a cataclysmic event. Picture this: when a positron meets an electron, they do not simply coexist. They annihilate each other, unleashing energy in a spectacular display. In that moment, their existence collapses into pure energy, releasing gamma rays, photons of extreme energy that dance through space at the speed of light. This remarkable transformation is an embodiment of Einstein's equation, which teaches us that mass can be converted into energy, illuminating profound truths about the universe. How often do we consider that the very fabric of the cosmos is engaged in a continuous cycle of creation and destruction, where particles and antiparticles embody the eternal struggle of existence? The energy released during matter-antimatter annihilation is nothing short of extraordinary. Just imagine the implications. A mere speck of antimatter, upon annihilation, can yield energy equivalent to that produced by a significant quantity of conventional fuels. This realization raises questions about our understanding of energy and the potential for harnessing this power. Would it be possible to tap into this cosmic well of energy? The scientific community has long pondered the practical applications of antimatter, envisioning a future where it could serve as a potent fuel source, perhaps for advanced space travel. What if one day, humanity harnesses the energy of antimatter, propelling us beyond our wildest dreams to explore the farthest reaches of the universe? As we explore further into the properties of antimatter, we encounter its fascinating interaction with magnetic fields. Antimatter behaves in ways that are strikingly similar to matter when subjected to magnetic forces, yet there is an exquisite twist. When antimatter particles move through a magnetic field, they experience a force due to their charge. For instance, positrons with their positive charge curve in one direction, while electrons with their negative charge bend in the opposite direction. This captivating divergence offers insight into the fundamental nature of charge and the symmetry between matter and antimatter. Imagine a laboratory where scientists create a cloud of antimatter. As positrons are confined within magnetic fields, they begin to exhibit this mesmerizing behavior, swirling and bending elegantly, almost as if performing a delicate ballet. This phenomenon is not merely academic. it holds potential for practical applications. By understanding how antimatter interacts with magnetic fields, we can develop sophisticated techniques for trapping and manipulating these elusive particles. This could pave the way for groundbreaking advancements in fields such as medical imaging, where positron emission tomography, or PET scans, already utilizes the annihilation of positrons to create detailed images of the human body. What drives this interplay between antimatter and magnetism? At a fundamental level, it speaks to the symmetries of nature, reflecting deeper truths about the laws that govern the universe. Scientists like Richard Feynman have often emphasized the elegance of these principles, suggesting that the universe is a grand stage where the laws of physics play out in a harmonious symphony. Each particle, whether matter or antimatter, adheres to these rules, engaging in a cosmic dialogue that captivates the imagination. As we ponder the remarkable properties of antimatter, we also uncover incredible stories of those who have dedicated their lives to understanding these phenomena. One such pioneer is the physicist Carl Anderson, who first discovered the positron in the early 20th century. His work opened the door to a new realm of exploration, allowing us to glimpse the intricate dance of particles and antiparticles. Anderson's dedication and curiosity inspired generations of scientists to delve deeper into the mysteries of antimatter, propelling our understanding forward. In our exploration of antimatter, we must also consider the implications of its properties on our understanding of the universe. Theoretical physicist Steven Weinberg once noted, "The more we learn about the universe, the more we realize how little we know." This sentiment resonates deeply as we examine antimatter, a substance that challenges our perceptions of reality and invites us to question our place within the cosmos. What other secrets lie hidden within the fabric of existence, waiting to be uncovered? Antimatter is a window into the unknown, a glimpse of the balance that sustains the universe. Each particle we study reveals layers of complexity, urging us to look beyond the surface. As we ponder the annihilation of antimatter and matter, we are reminded of our own existence, how our lives are woven into the cosmic narrative. The energy released during these annihilations is not merely an abstract concept. It represents the very essence of transformation, the cycle of life and death, creation and destruction. To fully appreciate the properties of antimatter, we must also acknowledge its rarity in our universe. Despite its intriguing characteristics, antimatter exists in minuscule quantities, a cosmic whisper amid the cacophony of matter. Why is this so? Some theories suggest that during the Big Bang, equal amounts of matter and antimatter were produced, yet somehow, a slight imbalance favored matter. This imbalance is a fundamental question in modern physics, prompting researchers to explore the underlying mechanisms that led to the dominance of matter in our universe. As we delve into these questions, we encounter a profound realization. Antimatter is not simply a scientific curiosity, but a vital key to understanding the cosmos. It embodies the duality of existence, the push and pull of creation and annihilation, and the delicate balance that sustains all that we know. Each time we witness the annihilation of particles, we are reminded of the intricate web of connections that bind us to the universe. In contemplating the properties of antimatter and its interactions, we find ourselves at the crossroads of science and philosophy. How does the existence of antimatter challenge our understanding of reality? What does it mean for our future as we strive to explore the cosmos? The stories of those who have ventured into the realms of antimatter serve as a beacon, guiding us toward deeper knowledge and greater understanding. As we reflect upon these ideas, we invite a sense of wonder to wash over us, soothing the mind and calming the spirit. The universe, with its mysteries and marvels, beckons us to explore, to inquire, and to embrace the unknown. In this journey, we are reminded that every particle, every interaction, holds a story waiting to be told, a truth waiting to be discovered. Antimatter's behavior in the realm of magnetic fields unveils yet another layer of its enigmatic nature. When we immerse ourselves in the world of charged particles, we discover that the forces at play are as intricate as they are beautiful. As antimatter particles, like positrons and antiprotons, glide through magnetic fields, they are subject to a force that compels them to follow curving paths, much like a leaf caught in a gentle eddy of water. This delicate interplay allows scientists to explore and manipulate antimatter in ways that were once thought to be mere science fiction. To imagine this phenomenon, picture a cloud of positrons drifting within a carefully crafted magnetic trap. As they navigate the field, their trajectories become a mesmerizing ballet of motion, reflecting the underlying principles of electromagnetism. The force acting on these charged particles is dictated by the Lorentz force law, a fundamental concept that describes how charged particles interact with electric and magnetic fields. This law not only governs the paths of positrons, but also provides profound insights into the behavior of antimatter, revealing the symmetry that exists between matter and its counterpart. The ability to control antimatter in magnetic fields opens the door to numerous possibilities. One such application lies in the realm of particle physics research, where scientists use sophisticated magnetic traps to study the properties of antiparticles. By confining these particles, researchers can observe their interactions with matter in a controlled environment, leading to new discoveries that challenge our understanding of fundamental physics. Imagine the excitement in a laboratory as researchers track the trails of positrons, piecing together the puzzle of antimatter's behavior, and perhaps unlocking secrets that have eluded us for generations. Moreover, the study of antimatter in magnetic fields extends beyond theoretical exploration. It has practical implications that touch our everyday lives. For instance, positron emission tomography, or PET scans, utilizes the annihilation of positrons to create vivid images of the human body. By injecting a small amount of radioactive material that emits positrons, medical professionals can obtain detailed insights into metabolic processes and detect anomalies within tissues. The intricate dance of antimatter and magnetic fields becomes a powerful tool in the diagnosis and treatment of medical conditions, illustrating how the properties of antimatter intersect with our human experience. As we contemplate these interactions, we might wonder about the broader implications of antimatter's behavior. What does it mean for our understanding of the universe? The study of magnetic fields and their influence on antimatter could potentially reveal additional symmetries in the laws of physics, shedding light on mysteries such as the asymmetry between matter and antimatter in the cosmos. The quest for understanding this imbalance is a driving force behind much of contemporary physics, prompting scientists to seek answers to questions that have lingered for decades. The allure of antimatter also invites reflection on the nature of existence itself. Physicist and cosmologist Lawrence Krauss eloquently remarked, "The amazing thing is that every atom in your body came from a star that exploded. And the atoms in your left hand probably came from a different star than your right hand. It really is the most poetic thing I know about physics. You are all stardust." This poetic notion resonates deeply when we consider that antimatter, in its fleeting existence, is part of the same cosmic fabric. The very particles that make up our universe are intertwined in a grand narrative, where matter and antimatter weave together stories of creation and annihilation. As we immerse ourselves in the study of antimatter's properties, we are invited to embrace a sense of wonder about the universe. Each interaction, each annihilation, serves as a reminder of the complexities that underpin our reality. The interplay of forces, the delicate balance between matter and antimatter, prompts us to reflect on our own relationship with the cosmos. What do we truly know about our place within this vast expanse? How do these particles, which are so elusive and rare, contribute to the grand tapestry of existence? The stories of scientists who have sought to unravel the mysteries of antimatter inspire us to continue our journey of exploration. They remind us that the quest for knowledge is a shared endeavor, a collaborative dance that transcends individual pursuits. As we ponder the intricacies of antimatter, we honor the legacy of those who have come before us, laying the groundwork for future generations of inquisitive minds to delve into the unknown. In this journey, we also confront the limitations of our understanding. Antimatter remains a tantalizing enigma, a substance that challenges our perceptions and compels us to question the very nature of reality. As we delve into the properties and interactions of antimatter, we must recognize that our exploration is not merely an intellectual exercise, but a profound invitation to engage with the universe on a deeper level. Each discovery brings us closer to understanding the cosmic balance that governs our existence. As we continue to explore the properties of antimatter and its interactions, we find ourselves at the intersection of science and philosophy. These reflections invite us to consider our place in the universe, to marvel at the intricate dance of particles, and to celebrate the mysteries that continue to unfold before us. What other wonders lie concealed within the folds of existence, waiting for us to uncover their secrets? The journey of discovery is endless, and the allure of antimatter serves as a guiding light, illuminating the path toward a greater understanding of the cosmos. Chapter 4: Antimatter in the Universe, Cosmic Implications. In the beginning, the universe erupted into existence, a cacophony of energy and potential. In those fleeting moments after the Big Bang, both matter and antimatter sprang forth, filling the cosmos with their opposing energies. This primordial generation set the stage for a universe rich with complexity and mystery. As matter began to coalesce into stars and galaxies, antimatter lingered in shadows, its role significant yet elusive. Antimatter's presence in the early universe raises profound questions. Why, amidst the vast creation of particles, did matter dominate? The symmetry of the universe suggests that equal quantities of matter and antimatter should have emerged. However, as we look around, we find ourselves surrounded by matter, with antimatter seemingly relegated to the background, a cosmic puzzle that has captivated scientists for generations. This asymmetry, often referred to as baryon asymmetry, intrigues physicists who seek to unravel its origins. Imagine standing on the precipice of the universe, gazing into its depths. What if every particle of matter had an equal counterpart in antimatter? How would that change our understanding of existence? The question lingers, inviting exploration. One of the most compelling aspects of antimatter is its relationship with dark matter, an enigmatic substance that makes up a significant portion of the universe. Dark matter, invisible yet influential, shapes galaxies and clusters through its gravitational pull. Some theories propose that antimatter could play a role in understanding dark matter's elusive nature. Picture a universe where dark matter is intertwined with antimatter, potentially offering answers as to why we cannot directly observe it. Theoretical physicists have contemplated the possibility that dark matter may consist of particles that interact with antimatter in ways we have yet to understand. This relationship could provide a pathway to uncovering the mysteries of the cosmos, where dark matter and antimatter coalesce in a dance of cosmic significance. As we explore the cosmos for evidence of antimatter, we find ourselves drawn to phenomena that hint at its existence. Cosmic rays, those high-energy particles racing across the universe, have been linked to the production of antimatter. When cosmic rays collide with particles in the Earth's atmosphere, they generate antiparticles, such as positrons and antiprotons. These ephemeral bursts of antimatter offer tantalizing glimpses into the universe's workings, illuminating our understanding of cosmic events. Consider the moment a cosmic ray strikes an atom in the atmosphere. The energy released creates a cascade of particles, a fleeting spectacle of creation. Scientists have observed positrons emerging from this process, confirming that antimatter is not merely a theoretical construct, but a tangible component of our universe. Beyond our atmosphere, evidence of antimatter appears in the form of gamma-ray bursts, intense flashes of energy that occur in distant galaxies. These bursts are thought to be the result of annihilation events, where particles of matter and antimatter collide, releasing energy in the form of gamma rays. As we trace the origins of these bursts, we encounter a universe alive with activity, a place where antimatter and matter engage in a cosmic ballet of creation and destruction. Imagine for a moment the immense energy produced during such interactions. This annihilation is not just a scientific curiosity, it's a reminder of the universe's power and the delicate balance of forces that govern it. When a positron meets an electron, they do not simply coexist. They annihilate, releasing energy that echoes through the cosmos. This transformation is a testament to the profound interconnectedness of matter and antimatter, a cycle of existence that has persisted since the dawn of time. As scientists delve deeper into the cosmic phenomena surrounding antimatter, they uncover more about its implications. For instance, researchers have detected antimatter in the form of positrons emanating from the center of our galaxy, hinting at processes that may involve black holes or neutron stars. These findings provide a glimpse into the energetic environments where antimatter thrives, suggesting that the universe is not just a backdrop for our existence, but a vibrant playground of interactions. Moreover, experiments conducted at particle accelerators on Earth replicate conditions akin to those of the early universe. In these giant machines, physicists collide particles at breakneck speeds, creating conditions where antimatter can be produced and studied. Through these experiments, they seek to understand the very fabric of reality, unraveling the mysteries of how antimatter behaves and interacts with its surroundings. In one such experiment, scientists created antihydrogen, the antimatter counterpart to hydrogen. This achievement marked a significant milestone in understanding the properties of antimatter. By comparing the behaviors of hydrogen and antihydrogen, researchers can explore fundamental questions about symmetry and the laws of physics. As we ponder the implications of antimatter, we are reminded of the words of a renowned physicist who once said, "If you want to find the secrets of the universe, think in terms of energy, frequency, and vibration." In this light, antimatter invites us to consider the universe not just as a physical space, but as a symphony of energies, frequencies, and interactions waiting to be understood. The journey of discovery reveals a cosmos where antimatter is not merely an anomaly, but an integral part of the narrative. Each positron discovered, each gamma-ray burst detected, adds to the story of our universe, a story that speaks of balance, beauty, and the quest for understanding. In contemplating antimatter's role in shaping our universe, we find ourselves drawn into the depths of cosmic wonder. The mysteries of antimatter intertwine with the fabric of reality, challenging our perceptions and inviting us to explore the unknown. With every question we answer, we unveil new layers of complexity, pushing the boundaries of what we know. In this vast expanse, where stars are born and galaxies collide, the dance of matter and antimatter continues. It is a dance that speaks to the very essence of existence, a reminder that the cosmos is alive with energy, and that we, too, are part of its grand design. The universe holds secrets within its depths, and as we journey through its realms, we discover not just the nature of antimatter, but also the profound connections that bind us to the cosmic tapestry. As we navigate through the vastness of space and time, the implications of antimatter ripple across our understanding of the universe. What lies beyond our current knowledge? What wonders await discovery? The answers remain just out of reach, shimmering like distant stars on the horizon, beckoning us to explore further into the heart of the cosmic mystery. As we ponder the intricate relationship between antimatter and the universe, we encounter the tantalizing mystery of antimatter asymmetry. This enigma doesn't merely prompt curiosity, it compels us to seek answers in the very fabric of cosmic existence. Why, in a universe that seems designed for balance, do we observe such a profound deficiency of antimatter? This question has led scientists down pathways of exploration that intertwine physics, cosmology, and philosophy. Consider the implications of this asymmetry. If matter and antimatter were created in equal quantities during the Big Bang, where did all the antimatter go? This puzzle has led to various theories, including those suggesting that antimatter might have fallen victim to processes that favored the survival of matter. Some propose that tiny variations in the behavior of particles and antiparticles during the early universe may have tipped the scales. The idea of CP violation, where the laws of physics differ slightly for matter and antimatter, serves as a key focus in this investigation. Imagine the universe as a vast arena of interactions, where even the slightest asymmetry can lead to significant outcomes. In this light, researchers have turned to particle accelerators, where they recreate conditions similar to those of the early universe. By smashing particles together at high energies, they can observe behaviors that may offer clues to the discrepancies between matter and antimatter. The hope is that these experiments will unveil the fundamental principles that govern our universe. Another intriguing avenue of exploration is the potential connection between antimatter and dark matter. While dark matter remains one of the greatest mysteries in modern astrophysics, some theories propose that antimatter could hold the key to unveiling its secrets. If we consider that dark matter interacts with normal matter primarily through gravity, could it also interact with antimatter in ways we have yet to discover? This thought invites us to reimagine our understanding of the cosmic landscape. Picture dark matter as a hidden thread weaving through the universe, influencing the formation of galaxies and the flow of cosmic structures. If antimatter exists in tandem with dark matter, could it be a missing piece in the puzzle? What if some dark matter particles are, in fact, antimatter? These questions challenge our perceptions and encourage us to broaden our horizons as we seek clarity in the shadows of the unknown. As we survey the heavens, observational evidence continues to emerge, hinting at the presence of antimatter in cosmic phenomena. Gamma-ray bursts, for instance, are not just harbingers of destruction, but also potential sources of antimatter. When massive stars reach the end of their life cycles, they can explode in supernovae, creating intense conditions that may produce antiparticles. The energy released during these cataclysmic events serves as a reminder of the universe's boundless energy and its capacity for creation. Envision a distant galaxy where a supernova has just erupted, casting its brilliance across the cosmos. In the aftermath of such an explosion, the annihilation of matter and antimatter could lead to a cascade of gamma rays, illuminating the darkness. Each burst we observe carries with it a symphony of signals, each note a potential insight into the processes that govern the universe. In addition to gamma ray bursts, researchers have also detected positrons in the vicinity of black holes. These enigmatic regions of space, where gravity reigns supreme, create environments ripe for the production of antimatter. As matter spirals into a black hole, it can interact with high-energy particles, leading to the creation of antiparticles that escape the intense gravitational pull. This phenomenon offers yet another glimpse into the cosmic interplay of matter and antimatter, further deepening our understanding of the universe. Moreover, as we explore our own galaxy, the Milky Way, we find evidence suggesting that antimatter may reside in unexpected locales. Observations from satellites designed to detect cosmic rays have revealed the presence of positrons emanating from regions near the galactic center. These findings challenge our assumptions about where antimatter might exist and raise new questions about the processes happening in these high-energy environments. What lies at the heart of these positrons? Are they the remnants of ancient stellar explosions, or do they hint at the presence of unknown cosmic phenomena? The answers may not be readily apparent, but each discovery adds a layer to our understanding of the vast universe. As scientists continue to probe the depths of space, they rely on advanced technologies and methodologies to uncover the secrets of antimatter. The journey is not merely about understanding particles. It is a quest to grasp the essence of existence itself. The tools of modern astrophysics, telescopes, particle detectors, and computer simulations are the instruments of this exploration, allowing us to peer into regions of space and time previously thought inaccessible. In this ongoing quest, the words of a distinguished physicist resonate. The important thing is not to stop questioning. Curiosity has its own reason for existing. This spirit of inquiry fuels the search for antimatter, propelling us into realms where the boundaries of knowledge blur and the allure of discovery beckons. As we delve further into the cosmic implications of antimatter, we find ourselves entangled in a web of questions and possibilities. The universe, with its vastness and intricacy, invites us to imagine new scenarios, to visualize the potential connections between matter, antimatter, and dark matter. Each observation, each experiment, is a step closer to understanding the underlying principles that govern our reality. What mysteries lie ahead? What revelations await in the uncharted territories of the cosmos? The journey is far from over, and the exploration of antimatter continues to unfold, illuminating the path toward a deeper comprehension of the universe and our place within it. Chapter 5: Antimatter and Black Holes, a Cosmic Connection. In the vast expanse of the cosmos, black holes stand as enigmatic giants, captivating our imagination and challenging our understanding of the universe. These colossal entities, formed from the remnants of massive stars that have exhausted their nuclear fuel, possess gravitational forces so powerful that not even light can escape their grasp. Yet, within this darkness, there lies the potential for the creation of antimatter, a phenomenon that sparks intrigue among astrophysicists. Imagine a black hole swirling with a tempest of matter spiraling towards its event horizon, the point of no return. As matter is drawn into this gravitational abyss, it accelerates and heats up, emitting radiation and high-energy particles in the process. This intense environment gives rise to the possibility that antimatter can be produced. Theoretical models suggest that when particles fall into a black hole, they can collide with other particles, potentially leading to the creation of antiparticles. This process could transform the energy of infalling matter into pairs of particles and antiparticles, weaving a connection between the dark heart of the black hole and the elusive nature of antimatter. Astrophysicists have proposed various mechanisms through which antimatter may manifest around black holes. One such model involves the interaction of high-energy cosmic rays with the intense gravitational field of a black hole. As these cosmic rays approach the event horizon, their energies transform, generating antiparticles that escape into the surrounding space. This creates a region where antimatter coexists alongside matter, a juxtaposition that defies our conventional understanding of the universe. Consider the implications of such interactions. If black holes can produce antimatter, what does this reveal about the fundamental processes governing our universe? The creation of antimatter jets is one of the most captivating aspects of this cosmic connection. When matter is consumed by a black hole, the immense energy can propel jets of particles at nearly the speed of light, some of which may contain antimatter. These jets, stretching across vast distances in the cosmos, are not just mere byproducts. They are windows into the energetic processes at play in the universe. The existence of antimatter jets suggests a dynamic interplay between matter and antimatter in the universe. Imagine witnessing a jet erupting from a black hole, a brilliant display of energy that signifies the depths of cosmic creation. These jets are often detected in the form of gamma-ray emissions, powerful bursts that illuminate the skies. The study of these emissions offers a glimpse into the fundamental workings of black holes and their ability to generate antimatter. Several observational studies have focused on detecting antimatter emissions from black holes. For instance, scientists have employed advanced telescopes to capture the gamma rays produced by these jets. By analyzing the signatures of these emissions, researchers can gain valuable insights into the conditions surrounding black holes. The detection of positrons, a hallmark of antimatter, within these emissions raises questions about the nature of the material being expelled. What cosmic forces are at play, and how do they contribute to the greater tapestry of the universe? Such inquiries lead us to consider the broader implications for astrophysics. The existence of antimatter around black holes could provide clues to the mysteries of dark matter and the asymmetry between matter and antimatter that pervades our universe. As scientists delve deeper into these phenomena, they are reminded of the words of a great physicist, who once said that the universe is not only stranger than we imagine, but stranger than we can imagine. The dance of particles near black holes may unlock secrets that challenge our understanding of physical laws. Theoretical physicists are exploring how the interactions between matter and antimatter jets may shape the very structure of galaxies. If black holes can produce antimatter, could this lead to regions in space where antimatter dominates? Imagine a galaxy teeming with antimatter, a mirror of our own, where the laws of physics play out in ways we have yet to comprehend. As we ponder these cosmic connections, the concept of antimatter continues to provoke wonder and curiosity. The potential for black holes to be factories of antimatter opens a new avenue for exploration in astrophysics. It compels us to question the very nature of the universe and our place within it. What if black holes are not merely destructive forces, but creators of a new realm of existence? The quest to understand the relationship between black holes and antimatter is ongoing, with each discovery unveiling new layers of complexity. Observational studies have begun to map the emissions from these enigmatic entities, revealing patterns that hint at the underlying processes. As telescopes peer into the depths of space, scientists are developing sophisticated models that incorporate the dynamics of black holes, matter, and antimatter interactions. The implications of these studies extend beyond the confines of theoretical physics. They inspire a rethinking of our cosmic narrative. What role do black holes play in the grand scheme of the universe? Are they merely endpoints for matter, or are they vital players in the cosmic cycle of creation and annihilation? As we reflect on the interplay of antimatter and black holes, we are reminded of the delicate balance that governs the universe. In this intricate web of forces, every black hole may possess the potential for creating antiparticles, connecting them to the very fabric of our existence. The mysteries of the cosmos beckon, inviting us to explore further and to embrace the unknown. In this ongoing journey, our understanding of antimatter continues to evolve. Each breakthrough, whether through theoretical modeling or observational discoveries, brings us closer to unraveling the cosmic connection between black holes and antimatter. The universe is rich with secrets waiting to be uncovered, and the pursuit of knowledge propels us forward, urging us to look deeper into the cosmos. As we gaze into the night sky, we are reminded that the dance of matter and antimatter is a reflection of the universe's complexity. The enigmatic nature of black holes intertwines with the elusive presence of antimatter, creating a narrative that inspires both awe and curiosity. What lies beyond the event horizon? What secrets do black holes conceal? As we ponder these questions, we find ourselves at the threshold of a magnificent cosmic adventure, eager to explore the connections that bind us to the universe. As we explore the potential for black holes to produce antimatter, we must consider the intricate processes that govern this phenomenon. The immense gravitational forces at play near a black hole create an environment ripe for particle interactions. In this cosmic crucible, matter is not merely consumed, but transformed. Imagine the chaos of particles swirling around the event horizon, colliding and merging, where energies can reach unimaginable heights. Theoretical physicists propose that under such extreme conditions, quantum fluctuations may lead to the spontaneous creation of particle-antiparticle pairs. This process, known as pair production, highlights the dynamic nature of spacetime near a black hole. Picture this. As energy surges through the surrounding space, a particle and its antiparticle emerge from the vacuum, momentarily existing before being drawn into the black hole's gravitational embrace. The interplay of these processes not only adds layers to our understanding of black holes, but also presents questions about the very fabric of reality. One of the most stimulating ideas is the concept of black holes acting as cosmic factories of antimatter. Consider the implications of this notion. If black holes can consistently produce antimatter, could they serve as sources of energy or even propulsion for future space travel? The potential for harnessing antimatter from these cosmic behemoths could redefine our exploration of the universe. As we reflect on the energy contained within antimatter, it becomes clear that understanding these processes could have profound consequences for humanity's future. Antimatter jets emanating from the regions surrounding black holes are particularly fascinating. These jets, composed of charged particles, can be propelled at incredible velocities, transporting energy across vast cosmic distances. Imagine witnessing one of these jets, a brilliant streak of light piercing the darkness as it races through the cosmos. The study of these jets extends beyond mere observation. It invites us to unravel the mechanisms that generate them. Researchers have been investigating the magnetic fields and accretion disks surrounding black holes, striving to understand how these factors contribute to the formation of jets. The existence of antimatter jets raises intriguing questions about the nature of cosmic evolution. How do these jets interact with the interstellar medium? Do they influence the formation of new stars and galaxies? Each jet serves as a messenger, carrying information about the black hole's environment and the conditions leading to its creation. As scientists analyze their properties, they piece together a larger narrative of cosmic evolution, where black holes play a pivotal role. Observational studies have begun to illuminate the enigmatic nature of these antimatter jets. Advanced telescopes equipped with sophisticated instrumentation are capturing the gamma rays emitted from these jets, allowing researchers to decipher their origins and composition. Imagine a team of scientists huddled around screens, their eyes glued to data streams that reveal the unseen dynamics of the universe. Each gamma ray burst represents a moment of discovery, a glimpse into the interactions between matter and antimatter in the shadow of black holes. Recent findings indicate that positrons, the antiparticles of electrons, have been detected in the emissions surrounding certain black holes. This tantalizing evidence suggests that antimatter is not merely a theoretical construct, but a tangible aspect of our universe. Could these emissions offer clues about the processes occurring within the black hole's accretion disk? What do they reveal about the energy transformations that take place? As researchers continue to analyze the data, they remain aware of the profound implications these discoveries hold for our understanding of fundamental physics. The study of antimatter emissions from black holes not only enriches our knowledge of astrophysics, but also prompts us to reconsider our place in the universe. If black holes are indeed producing antimatter, it challenges the conventional narrative of creation and annihilation. The balance between matter and antimatter, so carefully maintained since the dawn of the universe, may be influenced by these colossal entities. As we delve into this cosmic narrative, we encounter the idea of a universe that is richer and more complex than we can imagine. The existence of antimatter jets and their interactions with surrounding matter could be key to understanding the asymmetry between matter and antimatter that has puzzled scientists for generations. What if black holes, once viewed solely as destructive forces, are also creators of new cosmic phenomena? This evolving perspective invites us to ponder the interconnectedness of the universe. Imagine a cosmic web where black holes are not just endpoints, but pivotal nodes that facilitate the flow of energy and matter across vast distances. The dynamic interplay between these entities shapes the very fabric of the cosmos, influencing the formation of structures we observe today. As we reflect on the implications of black holes and their relationship with antimatter, we are reminded that our exploration is far from complete. Each discovery leads to new questions, propelling us deeper into the mysteries of the universe. The potential for antimatter jets to serve as tools for understanding cosmic evolution underscores the importance of continued research in this field. In this journey of exploration, the stories of the scientists who dedicate their lives to unraveling these mysteries resonate deeply. Their passion for discovery propels them into the unknown, echoing the sentiments of those who have come before them. The pursuit of knowledge becomes a shared endeavor, uniting us in our quest to comprehend the universe's most profound secrets. As we continue to gaze at the stars, we find ourselves captivated by the dance of particles and the enigmatic nature of black holes. The potential for new discoveries looms on the horizon, inviting us to embrace the adventure that lies ahead. What new insights await us in the cosmic depths? What untold stories will emerge from the interplay of matter and antimatter? The universe waits, a vast expanse of possibility, ready to reveal its wonders to those who dare to look. Chapter 6: Antimatter in Particle Physics, Experiments and Discoveries. The world of particle physics opens a door into the realm of antimatter, where experiments and discoveries illuminate the nature of the universe. At the forefront of this exploration is the European Organization for Nuclear Research, known as CERN. This bustling hub of scientific inquiry is home to the Large Hadron Collider, the most powerful particle accelerator in existence. Picture the vast subterranean ring, where particles hurtle toward each other at nearly the speed of light, colliding with immense energy. It is in these collisions that scientists have the opportunity to create and study antimatter in minute quantities, unveiling the secrets of its existence. One of the most significant achievements at CERN involves the creation of antihydrogen, the antimatter counterpart of hydrogen. Imagine a simple atom of hydrogen composed of a single proton and an electron. Now, envision its twin, antihydrogen, formed from an antiproton and a positron. The production of antihydrogen is not merely a laboratory curiosity, it holds profound significance for scientific studies. By understanding its properties and behaviors, researchers can test fundamental theories of physics, including the symmetries that govern our universe. The creation of antihydrogen is no easy task. Scientists at CERN employ a delicate dance of technology and precision. They first produce antiprotons by accelerating protons and smashing them against a target, generating a spray of particles. This process is akin to striking a bell and listening for the resonance of sound waves. The antiprotons are then captured and cooled, allowing them to combine with positrons. This intricate orchestration results in the formation of antihydrogen atoms, albeit for only brief moments. The fleeting existence of antihydrogen challenges researchers to capture its characteristics before it annihilates upon encountering matter, producing bursts of energy. Imagine standing in a laboratory where physicists are meticulously observing antihydrogen. They employ sophisticated techniques to trap these atoms using magnetic fields, creating a controlled environment to study their properties. One of the most compelling aspects of antihydrogen research is its potential to test fundamental symmetries in physics. Symmetry is a guiding principle in nature, governing interactions and behaviors. Scientists seek to understand whether antimatter behaves identically to matter under the laws of physics, or if subtle differences exist that could provide answers to long-standing questions. The behavior of antimatter is steeped in mystery. For instance, researchers explore whether antihydrogen falls at the same rate as hydrogen in a gravitational field. This inquiry relates to the principle of equivalence, a cornerstone of general relativity. Albert Einstein, the architect of modern physics, proposed that gravity affects all forms of matter equally. If antimatter exhibits different gravitational behavior, it could challenge our understanding of gravity itself. This line of inquiry invites us to ponder. What if the universe operates under rules we have yet to comprehend? What new dimensions of reality could unfold if antimatter obeys different laws? The study of fundamental symmetries also extends beyond gravity. Researchers investigate charge parity time symmetry, also known as CPT symmetry, which posits that the laws of physics should remain unchanged if particles are replaced by antiparticles, their spatial coordinates are inverted, and time is reversed. This profound concept anchors our understanding of particle interactions. However, if experiments reveal deviations from this symmetry in antimatter, it could unravel the delicate balance that sustains our universe and provide insights into the reasons behind the dominance of matter over antimatter. As we contemplate the implications of these experiments, we encounter the future of antimatter research. Scientists are not resting on their laurels, but are actively planning ambitious experiments to deepen our understanding. One such endeavor involves the ASACUSA collaboration at CERN, which aims to measure the properties of antihydrogen with unprecedented precision. Imagine a world where we can discern the minute differences between matter and antimatter, revealing new layers of reality. This pursuit could lead to groundbreaking revelations, reshaping our understanding of the universe and our place within it. Further afield, the ALPHA experiment is also making strides in antimatter research. This collaboration aims to explore the characteristics of antihydrogen, examining its spectral lines and comparing them to those of hydrogen. By scrutinizing these lines with high precision, scientists hope to uncover any discrepancies that may exist. Such differences could illuminate the fundamental forces that shape the cosmos and potentially offer insights into dark matter, a mysterious component that constitutes much of the universe. These ambitious projects are complemented by theoretical studies, as physicists model the behavior of antimatter and explore its implications for the universe. Theoretical frameworks are essential, guiding experimental designs and fueling the imagination of researchers. Could the exploration of antimatter lead us to new realms of technology, perhaps even harnessing its energy for future applications? The prospect of antimatter propulsion for space travel captivates the imagination, hinting at a future where the stars are within our reach. As we reflect on the discoveries and experiments that shape our understanding of antimatter, we are reminded of the importance of curiosity and inquiry. Each experiment conducted at CERN and beyond is a stepping stone toward unraveling the mysteries of the universe. The pursuit of knowledge is a journey without end, a quest that invites us to explore the unknown. Imagine the excitement that fills the air as researchers gather to discuss their findings, their minds buzzing with possibilities. Each piece of data collected represents not just a result, but a glimpse into the workings of the cosmos. The beauty of science lies in its ability to weave together questions and answers, creating a rich narrative that drives humanity forward. As we continue to delve into the world of antimatter, we stand on the threshold of discovery, ready to explore the depths of our universe. What mysteries will we uncover as we push the boundaries of our understanding? What will we learn about the nature of existence itself? The answers await us, shimmering just beyond our current knowledge, inviting us to take the next step in our cosmic journey. The exploration of antimatter at CERN is not merely a scientific endeavor. It is a profound inquiry into the very fabric of reality. As researchers peer into the heart of their experiments, they are not just uncovering the properties of antihydrogen, but also delving into the fundamental laws that govern the universe. The nuances of these experiments are a testament to human ingenuity and curiosity, revealing the delicate balance of forces that shape our existence. One fascinating aspect of antihydrogen research is its potential to unlock the mysteries of gravitational interactions. The quest to understand whether antimatter experiences gravity in the same manner as matter has profound implications. Envision the moment when antihydrogen is subjected to the force of gravity. Does it fall upwards, or does it mirror the behavior of its matter counterpart? This question has puzzled scientists and ignited the imagination of theorists. If antihydrogen behaves differently in a gravitational field, it could hint at new physics that extends beyond our current comprehension. The groundwork for these investigations of gravitational behavior is laid by the ambitious For Example Is experiment at CERN. This initiative aims to measure the gravitational interaction of antihydrogen by dropping it in a controlled environment. Picture the scene: antihydrogen atoms suspended in a magnetic trap, poised to be released into free fall. The data collected from such an experiment could dramatically reshape our understanding of gravity and antimatter, potentially leading to insights that bridge the gap between general relativity and quantum mechanics. Beyond gravity, the study of fundamental symmetries reveals another layer of the antimatter enigma. Scientists engage in tests of charge parity time, CPT symmetry, using antihydrogen to explore whether the universe's laws are truly symmetrical. Consider the implications of discovering slight deviations from this symmetry. Such findings could illuminate the reasons for the apparent imbalance between matter and antimatter, a conundrum that has eluded physicists for decades. The idea that the universe may harbor hidden asymmetries challenges us to reevaluate our understanding of the cosmos and our place within it. Meanwhile, the Alpha collaboration continues to refine its search for discrepancies in the spectral properties of antihydrogen. Imagine the precision equipment, finely tuned to detect the faintest whisper of difference between the light emitted by hydrogen and that emitted by antihydrogen. This meticulous work could yield invaluable data, revealing whether the forces that bind atoms are truly universal. If differences emerge, they may provide a window into the mysterious dynamics of dark matter and the fundamental structure of the universe. As scientists push the boundaries of what we know, they also ponder the practical applications of antimatter. Theoretically, antimatter could be harnessed as an incredibly potent energy source. The annihilation of matter and antimatter produces energy on an unimaginable scale, which has sparked discussions about its potential use in advanced propulsion systems for space travel. Picture a spacecraft powered by antimatter, capable of traversing the vast distances of the cosmos in a fraction of the time it takes conventional spacecraft. The idea is not just a dream. It represents the intersection of science fiction and the frontiers of physics. The future of antimatter research is bright, with ongoing experiments and collaborations worldwide. Beyond CERN, facilities like Fermilab in the United States and the Japan Proton Accelerator Research Complex are joining the quest to unveil the secrets of antimatter. These institutions are collaborating to create a global network of research, exchanging findings and ideas as they delve deeper into this intriguing field. Imagine the excitement in the air as researchers gather at international conferences, sharing their latest discoveries and theories. Each discussion fuels new questions, propelling the scientific community forward. The enthusiasm is palpable, a collective curiosity that binds scientists together in their shared pursuit of understanding. What new revelations will surface in the coming years? What technologies might emerge from our exploration of antimatter? As we contemplate the future of antimatter research, we are reminded of the interconnectedness of science and humanity's quest for knowledge. Each experiment is a chapter in an unfolding story, a testament to our insatiable curiosity and desire to understand the universe. The exploration of antimatter invites us to dream of possibilities previously thought unattainable, igniting our imaginations and inspiring future generations of scientists. The allure of antimatter lies not only in what we have discovered, but also in what remains hidden, waiting to be revealed. As we stand on the precipice of discovery, we are beckoned to continue our journey into the unknown. What lies ahead is an adventure that transcends the boundaries of our current understanding, inviting us to embrace the mysteries that await. The journey into the realm of antimatter is not just an exploration of particles. It is a quest for understanding the very essence of the universe. As we look ahead, the potential for new discoveries beckons, driven by the relentless pursuit of knowledge. The future experiments planned for antimatter research are ambitious, promising to peel back the layers of complexity that shroud our understanding. One of the most exciting prospects lies in the continued investigation of antihydrogen. The Alpha collaboration, for instance, is poised to enhance its precision measurements of antihydrogen's spectral properties. Imagine a team of scientists working tirelessly to capture light emitted from antihydrogen, analyzing the frequencies with instruments so sensitive that they can detect minuscule variations. This meticulous work aims to determine whether antihydrogen emits light at frequencies identical to hydrogen. If discrepancies arise, they could unveil new dimensions of physics, revealing secrets about the fundamental forces that govern our universe. Moreover, the For Example is experiment at CERN is set to explore the gravitational behavior of antihydrogen in groundbreaking ways. Picture the spectacle of antihydrogen falling freely in a vacuum, unhindered by external forces. This experiment seeks to determine if antihydrogen behaves like hydrogen under gravity, or if it reveals an unexpected divergence. Such findings could ignite a deeper understanding of gravity itself, challenging established notions and perhaps even reshaping the foundations of physics. Another tantalizing avenue of research involves the study of antimatter in cosmic settings. Scientists are planning experiments to investigate the production of antimatter in high-energy astrophysical environments, such as the vicinity of black holes and supernovae. Imagine the tumultuous dance of particles near a black hole, where extreme gravitational forces may facilitate the creation of antiparticles. Understanding how these environments contribute to antimatter production could bridge gaps in our knowledge about cosmic evolution and the life cycles of stars. Furthermore, the exploration of antimatter could lead to transformative technological advancements. Researchers are not only focused on fundamental questions, but are also envisioning applications that could arise from harnessing antimatter. The dream of antimatter propulsion for spacecraft is particularly captivating. Imagine a future where vessels powered by annihilation reactions can traverse interstellar distances in a fraction of the time it currently takes. This ambition is not merely a flight of fancy. It represents the intersection of imagination and scientific potential. As the scientific community continues to collaborate on these ambitious projects, the importance of global partnerships becomes ever more evident. Institutions around the world are dedicating resources to antimatter research, pooling expertise and technology to propel the field forward. The international nature of these collaborations fosters a vibrant exchange of ideas, driving innovation and discovery. In this unfolding story, the role of theoretical physicists is vital. They craft models and simulations that guide experimental designs, illuminating paths that may lead to groundbreaking insights. The interplay between theory and experiment is akin to a symphony, where each note contributes to a grander composition, echoing the mysteries of the universe. As we contemplate the horizon of antimatter research, it becomes clear that the journey is not just about the particles themselves, but also about the questions they pose. Each experiment invites us to challenge our assumptions and expand our understanding. What if antimatter reveals a deeper symbiosis between the forces of nature? How might our understanding of the cosmos evolve if we unlock the secrets of antimatter? The exploration of antimatter is a testament to human curiosity and our unyielding desire to comprehend the universe. Each discovery offers a glimpse into the interconnectedness of existence, urging us to ponder our place within the cosmic tapestry. The future is filled with promise, an invitation to embrace the unknown and to continue the quest for knowledge as we delve deeper into the mysteries that lie ahead. Chapter 7: Antimatter in Technology, Potential Applications. In the realm of technology, the intriguing properties of antimatter have begun to find their way into practical applications, particularly in medicine and space exploration. One of the most remarkable uses of antimatter is in the field of medical imaging, specifically through positron emission tomography, commonly known as PET scans. Imagine a world where the inner workings of the human body can be observed with exquisite detail, where diseases can be detected long before they manifest into significant health issues. This is the promise of PET technology, which harnesses the power of positrons, those tiny antiparticles that mirror electrons. When a positron is emitted from a radioactive isotope injected into the body, it encounters an electron. In this moment, the two annihilate each other, producing gamma rays that travel in opposite directions. These rays are detected by the PET scanner, allowing clinicians to create detailed images of metabolic processes within the body. This phenomenon is not just a testament to the capabilities of modern medicine, but also a profound illustration of how antimatter can offer insights into the most intricate biological mechanisms. The precision with which PET scans can identify tumors and monitor the effectiveness of treatments is a game changer in oncology. It allows for earlier interventions, tailored therapies, and ultimately, better patient outcomes. As we reflect on the implications of such technology, we might ask ourselves, how many lives could be improved through the continued exploration of antimatter applications in medicine? Beyond the boundaries of Earth, antimatter offers tantalizing possibilities for space travel. The concept of antimatter propulsion captures the imagination of scientists and engineers alike, presenting a vision of swift journeys across the cosmos. Imagine a spacecraft powered by antimatter, harnessing the energy released when antimatter meets matter. This propulsion system would provide thrust far beyond what conventional chemical rockets can achieve, reducing travel time to distant planets and even other star systems. The theoretical framework for antimatter propulsion involves the annihilation of positrons and electrons, resulting in an explosion of energy that could be converted into kinetic energy for the spacecraft. Envision a ship gliding seamlessly through the void of space, propelled by the very fabric of the universe's oppositional forces. The prospect of harnessing such power raises questions about our ability to explore and understand the cosmos in ways that were previously confined to the realm of science fiction. However, as we dream of these futuristic technologies, we must also confront the challenges that lie in our path. The production of antimatter is an exceedingly complex and energy-intensive process. Current methods yield only minute quantities of antimatter, requiring vast amounts of energy, often more than what can be produced by the annihilation itself. The cost and feasibility of producing sufficient antimatter for practical propulsion remain significant hurdles. Moreover, the containment of antimatter poses another formidable challenge. Antimatter cannot be stored in conventional containers, as it would annihilate upon contact with matter. Scientists have developed sophisticated magnetic containment systems, but these are still in the experimental stage and require further research to become viable for long-term storage. The theoretical implications of antimatter extend into energy generation, where the potential for harnessing its power could reshape our understanding of energy production. Imagine a world where energy could be generated from the annihilation of matter and antimatter, yielding clean, virtually limitless energy. The enormous energy density of antimatter suggests that even small amounts could produce significant power. In this vision, antimatter might serve as a catalyst for advanced energy systems. Picture power plants where antimatter is utilized to create energy through controlled annihilation, providing a sustainable alternative to fossil fuels. This could mitigate climate change and reduce our reliance on finite resources, ushering in a new era of energy generation. The possibilities are as vast as they are exciting, yet they remain theoretical at this stage. The journey towards harnessing antimatter for practical use is fraught with challenges. While the scientific community is making strides in understanding and utilizing antimatter, the road ahead is complicated. The sheer cost of production, the challenges of containment, and the need for further technological advancements must be navigated carefully. As we ponder the future of antimatter in our technological landscape, we are reminded of the words of pioneers in the field. Vision and curiosity drive progress. What potential breakthroughs await us as we continue to explore this captivating substance? How might the technological applications of antimatter change our world in ways we have yet to imagine? The exploration of antimatter is not merely a scientific pursuit. It is a journey that intertwines imagination with the potential for transformative change. Each discovery brings us closer to unlocking the secrets of the universe, illuminating a path filled with promise and possibility. Through the lens of antimatter, we glimpse the vast horizons of technology and human ingenuity. The potential applications of antimatter extend beyond the realms of medicine and propulsion, reaching into the very heart of energy generation. Envision a world where energy production is not only efficient, but also sustainable, powered by the annihilation of matter and antimatter. The energy density of antimatter is staggering. Just a minuscule amount could yield more energy than traditional fuels can provide. This prospect invites us to consider the revolutionary implications for our energy systems. Imagine power plants operating not on fossil fuels or even nuclear fission, but through controlled annihilation processes. In such a system, antimatter could serve as a catalyst, allowing us to tap into the foundational forces of nature. The annihilation of matter and antimatter produces energy in accordance with Einstein's equation, suggesting that the energy released is not only vast, but also clean. The byproducts of such reactions are primarily gamma rays, which, when harnessed correctly, could be converted into usable energy. However, the road to harnessing this power is paved with complexity and challenges. The production of antimatter remains an intricate process, requiring advanced technologies for both creation and containment. Currently, the methods available yield only minute quantities of antimatter, and the energy costs associated with its production are astronomical. As we contemplate these limitations, we might wonder, what innovations might arise to overcome these barriers? Scientists are exploring various avenues to improve antimatter production, including advancements in particle accelerators and more efficient methods of trapping antiparticles. The development of new technologies could revolutionize how we generate antimatter, making it more accessible and feasible for practical applications. Imagine if we could produce antimatter in quantities sufficient for energy generation, transforming our energy landscape and contributing to a more sustainable future. Yet, the challenges extend beyond production. Containing antimatter is a formidable task, as it cannot exist in direct contact with matter without annihilating instantly. Researchers have developed magnetic confinement systems using electromagnetic fields to encapsulate antimatter in a vacuum. While fascinating, these systems are still in their infancy, requiring further refinement and research before they can be applied on a large scale. The delicate balance of forces involved raises questions about the safety and efficiency of such technologies. As we reflect on the journey toward practical antimatter applications, it becomes clear that this pursuit is not merely a scientific endeavor, but a quest for innovation and understanding. The potential for breakthroughs in energy generation, propulsion, and medical technology intertwines with our fundamental quest to understand the universe. Each step forward in antimatter research brings us closer to unlocking the secrets of the cosmos and reshaping our technological landscape. In contemplating the implications of antimatter, we can draw inspiration from the visionaries who have paved the way for scientific progress. Their curiosity and determination have driven the exploration of the unknown, prompting us to ask bold questions and seek answers that lie just beyond our grasp. The journey of antimatter is an invitation to imagine a future where the limits of our understanding are continually pushed, where scientific inquiry transforms not only our technology, but also our very existence. As we stand on the brink of this exploration, we might ask ourselves, what breakthroughs await us in the field of antimatter? What new technologies could emerge from our understanding of this enigmatic substance? The path forward is filled with challenges, yet it is also rich with potential. The dream of harnessing antimatter for practical use continues to captivate the minds of scientists and engineers, breathing life into visions of a future where energy is abundant, space travel is within reach, and medical advancements are limited only by our imagination. Through the lens of antimatter, we glimpse a world where the possibilities are as vast as the universe itself. In this pursuit, we discover not only the potential for technological advancements, but also the essence of human curiosity, the driving force that propels us toward the stars and beyond. As we continue to explore antimatter, we are reminded that every discovery is a step closer to understanding the intricate dance of existence that shapes our reality. In this ongoing narrative, we find ourselves at a crossroads, where the challenges of antimatter meet the boundless potential of human ingenuity. The road ahead may be fraught with obstacles, yet it is illuminated by the promise of discovery and the thrill of exploration. What awaits us as we delve deeper into the mysteries of antimatter? Only time will tell, but the journey itself is a testament to our unyielding spirit and our quest for knowledge. Antimatter's potential to revolutionize energy generation invites us to consider not only the mechanics of annihilation, but also the broader implications of such a technology. Imagine a future where energy is clean and abundant, free from the limitations of fossil fuels and the dangers of nuclear waste. This vision hinges on our ability to effectively harness antimatter, turning the theoretical into reality. The energy density of antimatter is so high that even a small amount could power entire cities for extended periods. However, the daunting challenge lies in the practicalities of production and containment. As scientists work tirelessly to advance our understanding of antimatter, the journey is marked by both triumphs and setbacks. The quest for more efficient production methods continues, with researchers exploring innovative technologies such as laser cooling and advanced particle colliders. Each experiment brings us closer to unraveling the complexities of antimatter, shedding light on the potential that lies within. One must also consider the implications of successful antimatter energy systems on global society. What would it mean for developing countries, where access to energy is often limited? The ability to generate energy from antimatter could bridge gaps in energy equity, providing power where it is most needed. This transition could foster economic development and improve the quality of life for countless individuals. Yet, with such immense power comes responsibility. The ethical considerations surrounding the use of antimatter are profound. How do we ensure that such technology is used for the betterment of humanity rather than its detriment? The specter of misuse looms large, and as we move forward, the dialogue surrounding ethical guidelines must evolve in tandem with technological advancements. Moreover, the potential for antimatter propulsion systems in space travel cannot be overstated. Building on the earlier exploration of antimatter-powered spacecraft, we can envision missions that would take humanity further than ever before. Imagine sending a probe to the outer reaches of our solar system or beyond, propelled by the energy released from antimatter annihilation. The faster-than-light travel theorized in fiction may not be as far from reach as we once thought. The implications of antimatter propulsion extend to our understanding of interstellar travel. With conventional rockets, the vast distances between stars pose insurmountable challenges. However, an antimatter propulsion system could significantly cut travel times, opening the door to exploration of exoplanets and the search for extraterrestrial life. What mysteries might we uncover if we could travel to distant worlds in a fraction of the time it currently takes? As we stand at this crossroads of possibility, we must also recognize the scientific community's responsibility to ensure that such advances are pursued with caution and integrity. The challenges of antimatter, from production to containment, are not merely technical hurdles, but ethical dilemmas that necessitate careful consideration. In the spirit of exploration and discovery, we are reminded that the pursuit of knowledge is a journey without end. Each breakthrough in antimatter research brings us closer not only to harnessing its power, but also to understanding the fundamental nature of the universe. What lies ahead in our exploration of antimatter? As scientists continue to push the boundaries of what is possible, the potential applications of antimatter remain a canvas upon which the future of technology may be painted, vibrant, and full of promise. Through this lens, we can appreciate the delicate interplay between curiosity, innovation, and ethical responsibility. The unfolding story of antimatter is not just a narrative of scientific advancement. It is a testament to humanity's quest for understanding and the boundless potential that lies within the fabric of the universe. Chapter 8: The Philosophical and Ethical Implications of Antimatter. In the vastness of the cosmos, antimatter serves as a vital key to unlocking the mysteries that govern our universe. It is more than just a scientific curiosity. It plays a fundamental role in our understanding of existence itself. As scientists delve into the nature of antimatter, they unveil profound implications about the universe's origin, structure, and fate. Imagine standing at the edge of a great expanse, where every star represents a question, and antimatter is the answer waiting to be discovered. The existence of antimatter challenges our perceptions of the universe. If we consider the Big Bang, a moment of cosmic creation, both matter and antimatter sprang forth in equal measure. Yet, as we look around today, we see a universe dominated by matter, with antimatter largely absent. This imbalance raises philosophical questions. Why has matter triumphed over antimatter? What does this asymmetry reveal about the fundamental laws of nature? These inquiries invite us to reflect on the nature of reality and our place within it. As researchers explore these questions, ethical considerations emerge. The potential applications of antimatter research present both opportunities and dilemmas. On one hand, antimatter holds the promise of revolutionary advancements, from medical technologies to energy solutions. On the other hand, the implications of harnessing such power require careful contemplation. How should we proceed in our quest for knowledge? What responsibilities do we bear as we unlock the secrets of the universe? These questions resonate deeply, urging us to consider the moral dimensions of our scientific pursuits. Take the case of antimatter in medicine, specifically in the field of positron emission tomography. This technology exemplifies the delicate balance between innovation and ethical responsibility. While it offers incredible potential for diagnosing diseases, it also raises concerns about the energy required for antimatter production. The process is complex and costly, demanding resources that could be allocated elsewhere. What ethical guidelines should govern our use of antimatter in healthcare? How do we weigh the benefits against the costs? These questions remind us that progress must be accompanied by an awareness of its broader implications. Looking ahead to the future, the impact of antimatter on technology is bound to be transformative. Imagine a world where antimatter propulsion systems enable interstellar travel, making distant planets accessible to humanity. Theoretical models suggest that antimatter could provide the energy required for such journeys, propelling spacecraft at unprecedented speeds. However, the realization of such technologies is still in the realm of speculation. How do we balance ambition with caution? The pursuit of these technologies requires not only scientific ingenuity, but also a commitment to ethical stewardship. Public perception of antimatter adds another layer to this intricate tapestry. The mysteries surrounding antimatter often fuel misconceptions. Many envision it as a destructive force, thanks in part to its portrayal in science fiction. Yet, the reality is far more nuanced. Antimatter is not inherently malevolent. Rather, it is a natural component of our universe, one that offers insights into the fundamental workings of physics. Imagine explaining to someone that antimatter is not the villain of a cosmic narrative, but a partner in the dance of creation and annihilation. How can we foster a greater understanding of antimatter among the public to dispel myths and encourage curiosity? Education plays a crucial role in shaping the narrative around antimatter. By engaging with the public, scientists can illuminate the complexities of antimatter while emphasizing its potential benefits. Imagine a classroom filled with inquisitive minds, where the wonders of antimatter spark conversations about the universe's fabric. Through outreach and accessible communication, we can demystify antimatter, transforming fear into fascination. What if we redefine the conversation around antimatter, inviting a new generation to explore its possibilities? As we engage with these philosophical and ethical implications, we also confront the uncertainty that accompanies scientific advancement. The journey of discovery is fraught with unknowns, and as we push the boundaries of our understanding, we must remain vigilant. The history of science is marked by moments of brilliance and missteps alike. Reflecting on this, one might ask, how can we ensure that our pursuit of knowledge is guided by wisdom? This balance of intellect and ethics is crucial as we forge ahead into uncharted territory. Antimatter is not merely a concept confined to laboratory experiments or theoretical discussions. It is a bridge between the known and the unknown, a medium through which we can explore the very essence of existence. As we stand at this crossroads, we are called to foster a relationship with antimatter that transcends fear and embraces curiosity. What wonders await us on the other side of this inquiry? By nurturing a culture of exploration and responsibility, we can unlock the potential of antimatter while safeguarding the future of our planet and its inhabitants. The journey into the philosophical and ethical implications of antimatter invites us to reflect on the very nature of existence and our role within it. It is a call to action, urging us to engage with the complexities of the universe while remaining grounded in our ethical responsibilities. As we continue to explore this enigmatic substance, we must remain mindful of the profound questions it raises, shaping not only our understanding of the cosmos, but also our approach to the stewardship of knowledge itself. What legacy will we leave behind as we unravel the mysteries of antimatter? The answers lie in our hands, awaiting our exploration. Antimatter's role in shaping our understanding of the universe extends far beyond theoretical discussions. It serves as a powerful tool for probing the very fabric of reality, igniting curiosity and igniting profound questions about existence itself. The very nature of antimatter invites a contemplation of the universe's origins and the fundamental forces that govern it. What if the principles that dictate the behavior of antimatter could unravel the secrets of dark matter or dark energy, those elusive forces that seem to dominate the cosmos? Such possibilities captivate the minds of researchers, encouraging a relentless pursuit of knowledge. As scientists venture further into the enigma of antimatter, they are compelled to confront the ethical dimensions of their work. The potential applications of antimatter, especially in energy production, evoke a spectrum of responses. The allure of harnessing antimatter for energy is tantalizing. A tiny amount could yield energy equivalent to the output of a nuclear reactor. However, this prospect raises critical questions about safety, environmental impact, and the moral implications of such power. What safeguards must we implement to ensure that our quest for energy does not lead us down a path of destruction? Consider the thoughts of physicist Richard Feynman, who once remarked on the duality of science and ethics, suggesting that the scientist is not a person who gives the right answers, he's one who asks the right questions. This essence of inquiry underpins the ethical considerations surrounding antimatter research. The path ahead must be navigated with a balance of scientific ambition and ethical responsibility, recognizing that the power we wield comes with significant consequences. Moreover, the impact of antimatter on future technologies is poised to be transformative. Envision a world where antimatter drives propulsion systems that allow us to traverse the cosmos at unimaginable speeds. Theoretical frameworks suggest that antimatter could revolutionize space exploration, enabling humanity to reach distant planets and perhaps even habitable exoplanets beyond our solar system. The very thought of unlocking such potential stirs excitement, yet it prompts us to ask, what responsibilities accompany such breakthroughs? The exploration of antimatter's potential also invites us to reflect on our relationship with technology. As we stand at the precipice of new discoveries, we must question whether our pursuit of knowledge enhances our existence or poses risks to our future. The ethical landscape is complex, with the potential for both wondrous advancements and unforeseen consequences. How do we ensure that our advancements serve the greater good rather than narrow interests? As we consider the societal implications of antimatter research, public perception plays a pivotal role. Misconceptions abound, often fueled by sensational portrayals in popular culture. Many view antimatter as a dangerous force, a villain lurking in the shadows of science fiction narratives. Yet, this perception obscures the reality of antimatter's nature and potential. Antimatter is not an agent of destruction. Rather, it embodies the fundamental principles of physics that govern our universe. Imagine if we could reshape this narrative, transforming fear into fascination. The key lies in education and outreach, engaging the public in meaningful conversations about antimatter's implications. Through accessible communication, scientists can demystify antimatter, fostering a sense of wonder and curiosity. What if we inspired a new generation of thinkers, encouraging them to explore the mysteries of the universe with open minds? Collaboration between scientists and educators is crucial in this endeavor. By weaving together the threads of knowledge and understanding, we can cultivate a society that embraces scientific inquiry. Picture a world where students are empowered to question, to experiment, and to explore the wonders of antimatter. This vision invites us to consider how we can bridge the gap between complex scientific concepts and public understanding. In reflecting upon the philosophical and ethical implications of antimatter, we are reminded of the intricate relationship between knowledge and responsibility. The journey of discovery is not merely a quest for answers, but a responsibility to wield knowledge wisely. As we push the boundaries of our understanding, we must remain vigilant, recognizing that our actions today will shape the legacy we leave for future generations. What will we choose to do with the knowledge we uncover? The answers lie not only in the hands of scientists, but in the collective consciousness of society. By fostering a culture of curiosity and ethical reflection, we can approach the mysteries of antimatter with respect and awe, celebrating the boundless possibilities it presents. As we continue to explore the philosophical and ethical dimensions of antimatter, we are called to embrace a holistic perspective, one that honors the interconnectedness of science and humanity. The exploration of antimatter invites us to ponder our place within the cosmos, encouraging us to reflect on the profound questions that shape our existence. What stories will we tell about antimatter in the years to come? The journey is ongoing, and the universe whispers its secrets, waiting to be heard. The allure of antimatter extends into the realm of energy production, where its potential could redefine how we harness power. Imagine tapping into a source of energy so potent that a mere grain could fuel a city for days. This tantalizing prospect raises pivotal questions about our energy future. As we stand on the brink of such possibilities, we must consider not only the scientific feasibility, but also the ethical implications of wielding such power. What protocols must we establish to ensure that antimatter energy does not become a tool of destruction? The prospect of antimatter as an energy source is grounded in its annihilation properties. When matter and antimatter collide, the result is a release of energy that adheres to the principles of Einstein's equation. This event is not merely a physical reaction, it is an invitation to reassess our relationship with energy itself. How do we balance the promise of such a potent energy source against the potential hazards? The need for a robust ethical framework becomes paramount in guiding research and exploration in this field. Furthermore, the potential applications of antimatter extend beyond energy. Envision a future where antimatter catalyzes breakthroughs in transportation technology. The idea of antimatter propulsion for spacecraft has captured the imaginations of scientists and dreamers alike. Such technology could pave the way for voyages beyond our solar system, transforming the very nature of space exploration. Yet, with such ambitious aspirations come profound responsibilities. What safety measures must be put in place to ensure that the pursuit of interstellar travel does not lead to unintended consequences? The societal implications of antimatter research are vast, shaped in part by public perception and understanding. The narratives surrounding antimatter are often colored by sensationalism, with misconceptions perpetuated by popular media. Many view antimatter solely as a catastrophic force, a notion that oversimplifies its complex nature. It is crucial to foster a dialogue that emphasizes the scientific realities of antimatter while dispelling myths. How can scientists effectively communicate the benefits and risks of antimatter to a public that is often swayed by fear rather than knowledge? Education stands as a powerful ally in reshaping public perception. Imagine classrooms where students engage with the principles of antimatter, exploring its dual roles as both a scientific wonder and a potential risk. By incorporating antimatter into educational curricula, we can ignite curiosity and empower future generations to think critically about science. What if we could inspire a new wave of scientists who approach antimatter with an understanding of its ethical implications, ready to engage in responsible research? As we navigate the complexities of antimatter, we confront the philosophical underpinnings of our inquiries. The journey of discovery invites us to reflect on the nature of knowledge itself. Each advancement in our understanding of antimatter challenges us to reconsider what we know about the universe and our place within it. Is knowledge a gift that empowers us, or does it come with burdens that must be carefully managed? As we delve into these profound questions, we must remain mindful of the impact our discoveries have on humanity. Antimatter embodies the duality of existence, reflecting the intricate balance between creation and destruction. As we continue to explore its potential, we must strive for a harmonious relationship with this enigmatic substance. The path forward is illuminated by the wisdom gained from our inquiries, reminding us that our quest for knowledge must be accompanied by a commitment to ethical stewardship. What legacy will we forge as we unlock the mysteries of antimatter? The answers lie before us, waiting to be explored with courage and curiosity. Chapter 9: Antimatter in Fiction, Cultural Representations. In the realm of storytelling, where imagination intertwines with the threads of scientific inquiry, antimatter emerges as a compelling character. Its portrayal in science fiction literature and films captivates the audience, inviting them to explore the boundaries of possibility. As we journey through these narratives, we find that antimatter is not merely a scientific concept, but a vibrant element that enriches our understanding of the universe. Consider the vivid landscapes of science fiction, where antimatter often takes center stage. From the pages of novels to the grand visuals of cinematic masterpieces, it has been depicted as both a source of immense power and a harbinger of destruction. The allure of antimatter lies in its dual nature. It represents the potential for incredible energy release and the inherent dangers that accompany such power. Imagine a world where a small amount of antimatter could fuel a spaceship capable of traversing the stars at unprecedented speeds. This notion captures the imagination, illustrating humanity's relentless quest to push beyond the confines of its earthly existence. One notable example is found in the world of literature, where authors have woven antimatter into their narratives with remarkable creativity. In the renowned novel, The Three-Body Problem, the concept of antimatter is intricately tied to the unfolding of a cosmic drama. The author, Liu Cixin, uses antimatter not just as a plot device, but as a means to explore deep philosophical questions about civilization, survival, and the unknown expanse of the universe. How does the existence of antimatter shape our understanding of life beyond Earth? This question beckons the reader to ponder the implications of such discoveries and their potential impact on humanity. Similarly, films have embraced antimatter, often portraying it as a powerful tool or a catastrophic force. In Angels and Demons, based on Dan Brown's novel, antimatter is depicted as a weapon of immense destruction, capable of erasing entire cities. The film illustrates the fear and fascination that surround the idea of harnessing antimatter, a theme that resonates with audiences who are both intrigued by science and wary of its implications. How does our society reconcile the potential benefits of scientific advancements with the ethical dilemmas they may present? This tension between progress and caution is a recurring motif in narratives that engage with antimatter. The influence of fiction on the public understanding of science cannot be understated. These stories serve as a bridge, connecting complex scientific concepts to the broader populace. Through the lens of storytelling, antimatter becomes more than an abstract idea. It transforms into a familiar character, one that sparks curiosity and imagination. The narratives that incorporate antimatter often encourage audiences to contemplate the nature of reality itself. What if the laws of physics as we know them were to be rewritten? What if antimatter, rather than being a rare curiosity, became a commonplace element in our understanding of the universe. Such questions can evoke a sense of wonder, inviting listeners to explore the unknown. Notable works featuring antimatter concepts extend beyond mere fiction. They often reflect the scientific community's ongoing quest to understand this enigmatic counterpart of matter. The creative interpretations of antimatter in these stories can inspire scientific inquiry, encouraging budding scientists to dream of future breakthroughs. The interplay between science and imagination is particularly evident in the writings of Arthur C. Clarke, who famously said, "Any sufficiently advanced technology is indistinguishable from magic." This statement resonates deeply in the context of antimatter, as its potential applications often seem like magic to those unfamiliar with the underlying physics. As we explore the balance between science and imagination in storytelling, we find that the two realms are not mutually exclusive. Science fiction often serves as a precursor to actual scientific advancements, allowing us to envision what may one day be possible. Consider the early depictions of space travel in literature, which inspired generations of scientists and engineers to turn those dreams into reality. Similarly, the portrayal of antimatter in fiction can incite genuine scientific curiosity and innovation. The imagination sparked by these narratives has the power to shape public perception, making complex scientific concepts more accessible and engaging. However, this embrace of imagination must also come with a dose of scientific accuracy. While storytelling can stretch the boundaries of what we perceive as possible, it must also acknowledge the fundamental principles that govern our universe. The creative license taken by authors and filmmakers can sometimes blur the lines between reality and fantasy, leading to misconceptions about antimatter. For instance, the idea that antimatter can be easily harvested or utilized as a limitless energy source may give rise to unrealistic expectations. It is essential to ground these narratives in scientific understanding, ensuring that they resonate with truth while still captivating the imagination. As we reflect on the cultural representations of antimatter, we must also consider the broader implications of these stories. They invite us to contemplate our relationship with technology, power, and the unknown. Antimatter, with its immense potential and inherent risks, serves as a metaphor for the dual nature of scientific progress. How do we harness the benefits of technology while remaining mindful of the consequences? These stories challenge us to think critically about our choices and the paths we forge. In the tapestry of science fiction, antimatter stands as a symbol of both promise and peril. It encourages us to dream boldly while reminding us of the responsibilities that come with our discoveries. As we navigate through these narratives, we are invited to imagine a future where the mysteries of the universe are unveiled, where the delicate balance between matter and antimatter holds the key to our understanding of existence itself. Through the lens of fiction, we gain insight into the human experience, the quest for knowledge, and the ethical dilemmas that arise from our pursuit of scientific advancement. As we embrace the wonders of antimatter, we are reminded that the stories we tell have the power to shape not only our understanding of the universe, but also our place within it. Shall we dare to explore these narratives and allow them to guide us toward a deeper appreciation of the mysteries that lie ahead? Antimatter has woven itself into the fabric of modern storytelling, serving as a catalyst for imagination while simultaneously igniting curiosity about the principles of physics. This interplay between science and fiction not only entertains, but enlightens, fostering a deeper understanding of the complexities surrounding antimatter. It poses questions that resonate beyond the pages of novels or the frames of films. What is the nature of existence when both matter and antimatter vie for understanding in our universe? As we explore further, we find that science fiction has a unique ability to influence public perception of scientific concepts. The narratives that incorporate antimatter often simplify intricate theories, making them accessible to a wider audience. This democratization of knowledge allows individuals to engage with science in a way that feels personal and relatable. Imagine standing in a crowded room where conversations about the universe unfold, and amidst the chatter, the idea of antimatter becomes a topic of intrigue. It transforms from an abstract scientific term into a subject of everyday discussion, prompting questions and inspiring wonder. The impact of notable works featuring antimatter extends beyond entertainment. They often serve as a springboard for scientific inquiry, encouraging readers and viewers to explore the unknown. Take, for instance, the novel Contact by Carl Sagan, where the protagonist's journey is not only a quest for extraterrestrial life, but also an exploration of the limits of human understanding. In the story, the concept of advanced technology and the potential for communication across vast cosmic distances evokes a sense of possibility that echoes the scientific endeavors happening in real life. How do such narratives inspire future generations of scientists? They ignite a spark of curiosity, encouraging a spirit of exploration that leads to groundbreaking discoveries. The balance between scientific accuracy and imaginative storytelling is delicate yet essential. While creative liberties often embellish the realities of antimatter, they can also foster misconceptions. For instance, the portrayal of antimatter as a readily accessible energy source in films can lead to unrealistic expectations about its practical applications. It is crucial to remember that while antimatter holds immense potential, the current technology is still in its infancy. This gap between reality and fiction serves as a reminder of the importance of scientific literacy. How can we ensure that the excitement generated by these stories translates into a more profound understanding of science? By encouraging critical thinking and fostering an appreciation for the scientific method, we can cultivate a society that embraces inquiry and values knowledge. Consider the works of Philip K. Dick, whose stories often explore the nature of reality and perception. In The Man in the High Castle, he delves into alternate realities, prompting readers to question the very fabric of their existence. His narratives resonate with the philosophical implications of antimatter, as they invite contemplation about the nature of symmetry and the duality of existence. How often do we find ourselves grappling with the idea that our understanding is just one of many possibilities? The beauty of fiction lies in its ability to challenge our perspectives, urging us to consider the myriad paths that knowledge can take. The portrayal of antimatter in various stories often reflects the ethos of the time in which they were created. During the height of the space age, works like Star Trek introduced audiences to the concept of antimatter propulsion systems, igniting fascination with space travel and the exploration of the cosmos. The show's optimistic vision of the future, combined with its scientific foundations, inspired generations to dream of interstellar journeys. Can we trace the influence of such narratives on the actual advancements in space exploration? Indeed, the spirit of exploration that permeates these stories often mirrors the ambitions of scientists and engineers working tirelessly to turn fiction into reality. While fiction allows for boundless creativity, it is essential to maintain a foundation of scientific truth. The potential applications of antimatter, from advanced propulsion systems to medical imaging, are grounded in rigorous research and experimentation. As we reflect on the cultural representations of antimatter, we recognize that these narratives hold the power to shape public perception, either fostering excitement or perpetuating misconceptions. How do we strike a balance between wonder and reality? By embracing scientific inquiry and promoting education, we can ensure that the stories we tell about antimatter serve as a source of inspiration rather than confusion. In the end, the exploration of antimatter in fiction serves as a mirror reflecting our hopes, fears, and aspirations as a society. It challenges us to confront the unknown, to question the nature of reality, and to embrace the possibilities that lie ahead. Antimatter, with its dual nature of creation and destruction, embodies the essence of scientific progress, a reminder that our pursuit of knowledge is intertwined with the very fabric of existence. As we venture forth into the future, let us carry with us the lessons learned from these narratives, allowing them to guide our understanding of the universe and our place within it. Chapter 10: The Future of Antimatter Research, Challenges Ahead. Antimatter research stands on the brink of revolutionary potential, yet it grapples with profound challenges that demand our attention. One of the key hurdles lies in the production and storage of antimatter. Currently, the process of generating antimatter requires immense energy, far exceeding the energy produced by its annihilation with matter. This energy imbalance creates a paradox that hinders large-scale production. Imagine a laboratory where scientists work diligently to harness the power of particle collisions. In facilities like CERN, where high-energy collisions take place, only minuscule amounts of antimatter are created. These particles, such as antihydrogen, exist for mere moments before they interact with matter, resulting in annihilation. The fleeting nature of antimatter poses significant obstacles to both research and application. Storage presents another formidable challenge. Antimatter cannot be contained using ordinary materials. It must be isolated from matter altogether. Scientists employ complex magnetic and electric fields to trap antiparticles in a vacuum, creating what is known as a penning trap. Visualize a carefully orchestrated ballet of forces, where charged particles are suspended in a delicate balance, preventing them from colliding with the walls of their container. The intricacies involved in maintaining this environment are a testament to human ingenuity, but they also reveal the limitations of our current technology. Despite these challenges, the horizon is bright with potential breakthroughs. Researchers are continually exploring innovative methods to enhance antimatter production. One promising avenue involves advances in laser technology, which could facilitate more efficient creation processes. Imagine a scenario where lasers are fine-tuned to interact with particles in a way that maximizes the production of antiparticles. Such developments could drastically alter the landscape of antimatter research, making it not only more feasible, but also more practical for potential applications. Moreover, artificial intelligence and machine learning are poised to revolutionize our understanding of antimatter interactions. By analyzing vast amounts of experimental data, algorithms could uncover patterns and suggest new experiments that humans might overlook. Picture a future where AI acts as a collaborator in the quest for knowledge, helping scientists to navigate the complexities of antimatter behavior with newfound insights. Antimatter's role in future space exploration is equally captivating. As humanity gazes toward the stars, antimatter presents a tantalizing possibility for propulsion systems that could transcend our current limitations. The energy released during matter-antimatter annihilation is staggering, offering the potential for spacecraft to reach unprecedented velocities. Imagine a vessel fueled by antimatter, capable of traveling to distant planets in mere weeks rather than years. The dream of interstellar exploration could become a reality, transforming our understanding of the cosmos and our place within it. Antimatter could also aid in the search for extraterrestrial life. By launching missions equipped with antimatter-based technology, scientists could explore celestial bodies with greater efficiency. The ability to generate energy on-site using antimatter would allow for longer missions and deeper investigations of planets and moons that may harbor life. This vision of a future where antimatter serves as a catalyst for discovery invites us to ponder the implications of our exploration. However, the significance of continued research in antimatter science extends far beyond space exploration. Antimatter holds the key to answering some of the most profound questions about the universe. Why does the universe contain more matter than antimatter? What insights into fundamental physics can be gained from studying antimatter? As scientists probe these questions, they illuminate the very fabric of reality itself. The implications of antimatter research resonate deeply within the broader scientific community. Each discovery, no matter how small, contributes to our cumulative understanding of the universe. The pursuit of knowledge is akin to piecing together a grand puzzle, where each fragment reveals a glimpse of the bigger picture. Imagine being part of that journey, where the thrill of discovery fuels the passion to understand the cosmos. Moreover, the potential applications of antimatter could usher in revolutionary advancements in various fields. Beyond space exploration, these applications may extend to energy production, medical technologies, and even fundamental physics research. As scientists continue to unlock the mysteries of antimatter, they pave the way for innovations that could reshape our world. As we navigate this landscape of possibility, we must also recognize the ethical considerations that accompany such powerful knowledge. The responsible use of antimatter, particularly in the context of energy applications, raises questions about safety and sustainability. How do we harness this power without endangering ourselves or the planet? The dialogue surrounding these issues will be essential as we move forward. Antimatter research stands at a crossroads, where the challenges of production and storage meet the promise of extraordinary breakthroughs. The future beckons with possibilities that could redefine our understanding of the universe and our place within it. As we ponder the role of antimatter in space exploration and beyond, we find ourselves on the cusp of a new era of scientific inquiry, one that invites us to dream big and reach for the stars. The significance of this research cannot be overstated. It represents humanity's relentless quest for understanding, a journey that may one day illuminate the mysteries of existence itself. The current landscape of antimatter research is not without its challenges, particularly in the realms of production and storage. Scientists face the daunting task of generating sufficient quantities of antimatter while simultaneously ensuring its integrity during storage. The energy requirements are staggering, and the production rates are painstakingly slow. Yet, the quest for more efficient methods continues to inspire innovation. Consider the potential of using advanced particle accelerators that could operate at higher energies, or even the exploration of new materials that might improve the efficiency of magnetic confinement. Each advancement brings humanity a step closer to harnessing the potential of antimatter, which could fundamentally alter our energy landscape. Imagine a future where antimatter is produced sustainably and stored with minimal loss, opening doors to applications we can hardly fathom today. As researchers press on, they remain hopeful for breakthroughs that could transform the field. One such promising avenue is the development of new techniques for manipulating antimatter at the quantum level. This could lead to the creation of more stable antimatter particles, or even the possibility of creating larger quantities in a controlled environment. The idea of utilizing quantum entanglement to maintain antimatter states is an area of research that fuels the imagination. Picture a world where scientists can control antimatter with the finesse of a conductor guiding an orchestra, orchestrating interactions that were once thought impossible. The potential breakthroughs on the horizon are not limited to production methods. The exploration of antimatter's properties continues to yield fascinating insights. Research into the behavior of antimatter under extreme conditions, such as high temperatures or intense gravitational fields, could reveal secrets about the fundamental laws of physics. Scientists are also investigating how antimatter interacts with dark matter, which, as we have learned, constitutes a significant portion of the universe's mass. The interplay between these two enigmatic substances could unlock new pathways in our understanding of the cosmos. In the context of space exploration, antimatter's prospects are particularly exhilarating. Imagine a spacecraft powered by antimatter engines, where the energy produced would propel humans beyond the confines of our solar system. The energy density of antimatter is unmatched. Even a minuscule amount could propel a vehicle at speeds that would revolutionize space travel. This is not merely science fiction, but a tantalizing glimpse into what could become a reality. Antimatter propulsion systems could enable missions to Mars that take a fraction of the time currently required. Such advancements would make it feasible to establish a human presence on other planets, facilitating research and exploration beyond Earth. Picture astronauts embarking on missions that, with the aid of antimatter, could last only weeks instead of months, maximizing their ability to conduct experiments and gather data. Moreover, the potential for antimatter to power deep space missions opens up possibilities for exploring the outer planets and even beyond. The quest for knowledge about distant celestial bodies, such as the icy moons of Jupiter and Saturn, could be accelerated significantly with the application of antimatter technology. What mysteries lie hidden beneath the icy crust of Europa or in the dense atmosphere of Titan? With antimatter, we might soon be able to uncover these secrets. Beyond exploration, the implications of antimatter research extend into terrestrial applications. Medical technologies, particularly in diagnostics and treatment, stand to benefit immensely from advancements in antimatter science. Positron emission tomography, already a cornerstone of modern imaging, could see enhanced capabilities, allowing for more precise and earlier detection of diseases. Imagine the potential for personalized medicine, where treatments are tailored not only to the disease, but also to the individual's unique biological makeup, guided by insights gained from antimatter interactions. As we consider the significance of continued research in antimatter science, we find ourselves at a crossroads of ethical and philosophical inquiry. The exploration of antimatter is not just a scientific endeavor. It is a reflection of our innate curiosity and desire to understand the universe. As we push boundaries, we must also grapple with the potential consequences of our discoveries. The dialogue surrounding the responsible use of antimatter in energy production, for instance, is crucial. How can we ensure that the benefits outweigh the risks, particularly in an era where sustainability is paramount? Moreover, the ethical implications of antimatter research extend into its potential applications in weaponry. The destructive power of antimatter is profound, and we must remain vigilant in our pursuit of knowledge, ensuring that our advancements serve to enhance life rather than threaten it. The questions we face today will shape the future of antimatter research and its place in society. Antimatter research invites us to dream of a future rich with possibilities. It compels us to ask questions that challenge our understanding and inspire us to seek answers. As we explore the depths of this fascinating field, we find ourselves not only on a scientific journey, but also on a philosophical one that could redefine our very existence. Imagine the legacy we could leave behind, one where the mysteries of the universe are unveiled through the lens of antimatter, illuminating the path for future generations. As we stand on the brink of this new era, it becomes clear that the challenges we face are not insurmountable. The spirit of inquiry that has driven humanity from the dawn of civilization is alive and well. With each experiment, each breakthrough, we inch closer to unraveling the mysteries of antimatter. The interplay of curiosity, ethics, and scientific endeavor underscores the importance of this research. In the grand tapestry of the universe, antimatter may prove to be the key that unlocks the deepest secrets of existence, guiding us toward a future filled with wonder and discovery. The unfolding narrative of antimatter research is one that holds the promise of profound advancements, yet it is underscored by the weight of significant challenges. As scientists forge ahead in their quest for knowledge, they face not only the technical hurdles of antimatter production and storage, but also the broader implications of their discoveries. These implications resonate deeply across disciplines, inviting us to reflect on the role of antimatter in our understanding of the universe. Among the exciting prospects on the horizon is the potential for harnessing antimatter as a clean energy source. Imagine a world where the annihilation of antimatter could provide a virtually limitless supply of energy, far surpassing the capabilities of traditional energy sources. The clean and efficient nature of antimatter energy production could revolutionize power generation and consumption, offering a sustainable alternative that mitigates the environmental impacts we face today. This vision is not mere fantasy. It is a tantalizing glimpse into a future that could be realized through continued research and innovation. Furthermore, the intersection of antimatter research with quantum computing offers intriguing possibilities. Quantum computers, which leverage the principles of quantum mechanics, could potentially simulate antimatter interactions with unprecedented accuracy. The ability to model these complex behaviors could unlock new pathways in both fundamental physics and applied sciences. Picture a future where quantum simulations provide insights that lead to breakthroughs in antimatter production techniques, allowing for more effective storage methods and enhanced safety protocols. This synergy between quantum computing and antimatter research could accelerate our understanding, propelling us into realms of knowledge previously thought unattainable. The role of collaboration in the pursuit of antimatter research cannot be overstated. International partnerships among scientists and institutions are vital in pooling resources, knowledge, and expertise. Imagine the collaborative efforts of researchers from diverse backgrounds, coming together with a shared vision to unravel the mysteries of antimatter. This collective endeavor fosters an environment ripe for innovation, where ideas can flourish and breakthroughs can emerge. The global community of scientists is united by a common purpose: to explore the frontiers of antimatter and to harness its potential for the benefit of all humankind. As we contemplate the future of antimatter research, it is essential to remain cognizant of the ethical considerations that accompany such powerful knowledge. The discussions surrounding the responsible use of antimatter technology must engage scientists, ethicists, and policymakers alike. What safeguards can be established to ensure that the incredible potential of antimatter is harnessed for the greater good? How do we balance the pursuit of scientific advancement with the imperative of public safety? These questions demand thoughtful answers as we navigate the complexities of this new frontier. In the context of space exploration, the potential applications of antimatter technology extend far beyond propulsion systems. Consider the possibility of using antimatter as a power source for habitats on other planets. This could allow for sustainable living conditions that support long-term human presence beyond Earth. Picture colonies on Mars or moons of Jupiter, equipped with advanced antimatter technology, where humans can thrive, conduct research, and discover the secrets of the cosmos. The implications for exploration and colonization are profound, reimagining our relationship with the universe. Moreover, the potential for antimatter to contribute to our understanding of dark matter and dark energy cannot be overlooked. As we ponder the mysteries of the universe, antimatter may offer clues about the elusive components that govern much of its structure and behavior. By studying the interactions between matter and antimatter in the context of dark matter, scientists could unlock a deeper understanding of the fundamental forces at play. This line of inquiry holds the key to answering some of the most pressing questions in modern astrophysics. In summary, the future of antimatter research is a landscape rich with possibility. The challenges of production and storage are formidable, yet they are met with the unwavering spirit of inquiry and innovation. As we look to the horizon, we find ourselves at the intersection of science and imagination, where the pursuit of knowledge invites us to dream of a future filled with discovery and understanding. The journey ahead is one that beckons us to explore the uncharted territories of antimatter, illuminating pathways that may lead to transformative advancements in our world.